Two machines built to last 5 years are still calling home from the dark, and what they're reporting doesn't sound like the edge of our world. Voyager didn't just leave the planets behind, it ran into a boundary that moved, breathed and rewrote where the Sun's kingdom ends. So what did Voyager actually cross out there? And if the frontier of our solar system was never where we drew it, what else have we been wrong about? A faint carrier tone, thinner than a whisper, is still being pulled from the sky by dishes the size of buildings. It has crossed an ocean of noise to reach us, and it is older than the world that first learned to listen. To hear it at all, engineers do not simply receive a signal, they rescue coherence from randomness second by second. Atomic clocks hold time steady while Earth turns, atmospheres shimmer, and interference crowds the bands where Voyager speaks. The data rate collapses to a trickle, yet the meaning survives, because meaning was engineered into the link. Voyager's cameras once gave us faces of moons and the architecture of rings, but its longest mission is stranger. As power dwindles, the spacecraft becomes a disciplined instrument, measuring what cannot be photographed. Particles, fields, and plasma, subtle gradients in invisible weather, begin to sketch the Sun's influence as a living shape. What emerges is not a simple map with a neat border, but a domain that swells and tightens with solar seasons, a place where the wind from our star slows, heats, and tangles, where turbulence becomes a kind of language. And beyond that, a medium older than the solar system itself presses inward, shaping the frontier from the outside. Yet Voyager is more than a sensor platform drifting into darkness. It is also a deliberate artifact. A gold-plated record rides its frame with sounds, images, and greetings, an introduction to a species that expects to be temporary. The cover carries a key written in physics, and an address written in pulsars, as if the galaxy were a clock. This documentary follows the mission as two parallel stories that keep converging. One is the practical struggle to keep a failing machine pointed at Earth across billions of kilometers, as each watt becomes an argument. The other is the scientific struggle to define a boundary that refuses to behave like a wall. Along the way, we will meet the rare celestial timing that made the Grand Tour possible, and the gravity tricks that turned planets into engines. We will see how conservative design, redundancy, and ruthless power triage stretched a few years into half a century. We will enter Jupiter's lethal magnetosphere and hear its radio scream, then watch fire and ice rewrite what active and habitable can mean. We will drift through Saturn's rings as a physics problem made visible, and approach Titan behind its orange veil. We will follow Voyager 2 alone into the dim realm of Uranus and Neptune, where odd magnetic fields and unexpected weather challenge every tidy model. And then the images fall away, and the true suspense begins. With only instruments and inference, Voyager will trace the Sun's last defences against the galaxy, revealing how big our home really is and how uncertain its edges remain. Somewhere in that measurement lies a quieter conclusion about us, not as masters of a finished map, but as passengers on a temporary island of light. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From a rescued whisper in the Deep Space Network to the last planetary flybys, we'll follow Voyager's path step by step, then push into the unseen frontier. What it finds there will not be a single photograph, but a new way to locate ourselves in the galaxy. A faint, steady tone rides the noise floor, almost indistinguishable from space itself. On Earth, Deep Space Network antennas keep turning, slow, deliberate, and precise, narrowing their beams until a whisper becomes a trackable point. In control rooms lit by monitors and muted urgency, technicians watch a carrier line tremble inside a sea of static. The tone is not music, not speech, not even data yet. It is proof that a transmitter still oscillates. The transmitter is weaker than a light bulb, yet it crosses billions of kilometers. By the time it reaches Earth, its power has spread thin over an expanding sphere, so thin that the receiving dish must behave like a microscope. That is why the antennas integrate, stacking seconds into meaning, and why the signal processing is as important as the spacecraft. A narrow-band tone can be teased out of noise because randomness averages away, while coherence, however faint, persists. The signal arrives thinned by distance, bent by plasma, and threatened by every failure mode time can invent. Charged particles in the solar wind refract and scintillate the radio wave, adding phase jitter that engineers must model and subtract. Even Earth adds complications because our atmosphere, our rotation and our own radio emissions create a moving, imperfect listening platform. The Deep Space Network compensates with atomic clocks, Doppler predictions, and a choreography of handoffs between continents. This is the paradox at the start of Voyager's story. 2 spacecraft built for a short mission are still alive, still answering, still spending the last watts of their power budget with the caution of a ship on its final stores. Their voices are small, but their implications are huge. If we can still hear them, then the experiment is still running, and the edge of our world is still being measured. Voyager 1 and Voyager 2 were launched as planetary explorers, but they became something stranger. They became test particles, thrown outward to trace the sun's influence like dye in a current, revealing invisible flows through their changing surroundings. In physics, a test particle is small enough not to disturb what it measures, yet persistent enough to sample the field. Voyager is that idea made mechanical, an instrument package moving through gradients of plasma density, magnetic orientation, and particle energy. They also became time capsules, carrying the first intentional interstellar messages. Not a broadcast aimed at a target, but a bottle cast into a cosmic ocean, trusting that motion and time can deliver what intention cannot. Bolted to each spacecraft is a gold-plated copper disc, the Golden Record. It is an artifact, a metaphor, and a wager that physics can bridge ignorance, even when biology, culture, and language cannot. The record holds sounds of Earth that do not need translation to be felt. Wind and thunder, footsteps, laughter, a baby's cry, and the pulse of machines, signals of atmosphere, gravity, and hands shaping matter. Those sounds are not merely sentimental, because they encode a planet's physical processes in familiar forms. A thunderclap implies convection and charge separation, while surf implies a moon, tides, and a world with liquid boundaries. It holds music chosen to suggest a planet's range of pattern and emotion. The selections move from structured harmony to raw rhythm, implying that our minds search for order, then break it, then rebuild it again. It holds greetings in many languages, each one a claim that we existed. The variety is the point, many tongues, many cadences, because a single voice would imply a single world, and Earth is not that. It holds images encoded as analog signals, meant to be reconstructed by a patient mind. Anatomy and landscapes, mathematics and tools, a species trying to describe itself through shapes, proportions, and repeated motifs. The images are not stored as pixels in a modern sense, but as a continuous waveform that can be scanned into lines. That choice assumes the recipient can build a simple decoder, an elegant bet on engineering rather than shared aesthetics. Even the cover is a message, designed as a decoding key rather than a poem. It assumes the recipient understands measurement, frequency, and the universality of atoms because those are the few concepts that travel well. At the top is the hydrogen hyperfine transition, a clock made from the most common element. It defines time and length, anchoring the rest of the diagram to a natural frequency, 1420 MHz, rather than a human convention. Hydrogen's hyperfine line is not arbitrary, because it comes from a quantum flip in the atom's lowest energy state. In plain terms, it is a built-in metronome of the universe, and it lets the record define units without translation. A pulsar map points outward like a galactic address, using the periods of millisecond lighthouses. If those periods are measured, the origin can be triangulated in space and time, because pulsars slow predictably as they lose rotational energy. Each line on the map carries a binary number, encoding a pulsar's period as a kind of timestamp. It is an attempt to say not only where we were, but when we were, because the galaxy itself is not static. A schematic of the solar system shows the launch point and the trajectories, a simple geometry of departure. It implies a star, a set of planets, and a direction of travel, with the spacecraft leaving on paths that will not loop back. The diagram is modest, almost clinical, yet it carries a quiet drama. It shows a civilization that learned to use gravity as a tool, and then used that tool to throw a message beyond its own weather. These are two messages in a bottle, but they only matter if the bottle survives. The Golden Record is silent without the spacecraft that carry it beyond our neighbourhood, and metal alone cannot guarantee endurance. Survival means thermal balance, attitude control, and a radio link that can outlast decades of drift. It means components aging under radiation, lubricants drying, and solder joints enduring cycles of heat and cold without a second chance. The spacecraft themselves are the other message, written in telemetry and in their changing environment. Each bit of data says where the sun's domain weakens and what replaces it, turning distance into a set of measured transitions. That is the stake of this documentary, and it is bigger than nostalgia for a famous mission. Voyager is a slow-motion experiment in cosmology, run at the scale of a star, with results that cannot be rushed. We live inside a bubble carved by the sun, inflated by the solar wind and shaped by the galaxy. The solar wind is a supersonic outflow of charged particles, and it drags the sun's magnetic field outward into a spiraling sheet. That bubble is not a hard wall, but a pressure balance between outflow and interstellar resistance. Where the wind weakens, it slows and heats, and its magnetic field compresses, like a river meeting a standing tide. For centuries we argued about the boundary, because we could not touch it. Telescopes could infer, theory could sketch, but without a probe there was no way to sample the plasma directly, or to feel the magnetic field change. Voyager could touch it by leaving it, and by reporting the conditions as it went. The solar system becomes a measurable structure inside the Milky Way, not just a diagram because numbers replace metaphors. The central question is simple to ask and hard to answer. What did Voyager ultimately find about the true size of the sun's domain, and what lies beyond its edge? The hook is that the most surprising find is not a planet. It is the shape, behaviour and fragility of the sun's protective bubble, and the strange physics at its boundary, where familiar rules keep working, but in unfamiliar combinations. At first, that sounds like a technical footnote compared with Jupiter's storms or Saturn's rings, yet the bubble decides how cosmic radiation enters our system, and how our star interacts with the galaxy, which has a quiet influence on every orbit. Cosmic rays are not just abstract hazards, because they are high-energy particles that can penetrate materials and damage electronics. The heliosphere modulates their intensity, acting like a variable shield whose thickness depends on solar activity. It is also a boundary that refuses to behave like a clean shell. It is dynamic, asymmetric, and sensitive to storms from the sun and pressure from interstellar space, so the edge can move like a breathing surface. The sun is not steady, because its magnetic polarity flips on an approximately 11-year cycle. Those changes propagate outward as waves and shocks, and they can reach the boundary years later, reshaping it long after the original solar outburst. Voyager's long life turns that boundary into a story with chapters. The mission begins with planetary revelations, then shifts outward to the heliosphere, then to the heliopause, where the solar wind finally yields. Beyond that is the local interstellar medium, not empty but thinly populated with charged particles and magnetic fields. The phrase beyond the edge hides a complex transition region, where particle populations mix and magnetic directions compete. In that region, the density is low, yet the energies can be high, and the magnetic field can be surprisingly coherent. It is a reminder that space is not nothing. It is a material with pressure, conductivity, and structure. Voyager 2 crossed that region with instruments still working, sampling plasma and fields directly. Its plasma instrument could still measure the solar wind's speed and temperature, so the crossing could be identified with fewer assumptions. Voyager 1 crossed earlier with a different set of tools, forcing scientists to infer missing pieces. When its plasma instrument stopped functioning, researchers leaned on magnetic field signatures and particle counts, evidence that is indirect, yet persuasive. Together they provide two cuts through the same phenomenon, separated by time and direction. Two paths, two data sets, and one stubborn boundary that does not match expectations. Because the heliosphere is shaped by the interstellar wind like a weather front, the distance between Earth and the spacecraft is so large that even light takes hours to cross it. Commands crawl outward, and replies crawl back, making every interaction a delayed conversation, where confirmation arrives long after the decision. That delay changes how you operate a spacecraft because you cannot steer in real time. Engineers must predict the craft's state, send a sequence and wait, hoping that the machine executes it exactly as intended. The link is fragile because the spacecraft are old and because power is finite. Radioisotope generators decay, heaters shut off, instruments go cold, and engineers ration every watt, choosing what to keep alive and what to let go. Those generators are not batteries, but thermoelectric systems driven by the heat of radioactive decay. As the isotope's output falls, the spacecraft must shed loads, and every shutdown is a permanent narrowing of what can be learned. The link is fragile because the universe is loud in its own way. Solar plasma can distort signals, Earth's rotation changes geometry, and the DSN must share time across many missions, each one competing for the same quiet listening hours. Even the spacecraft's own motion complicates the radio, because velocity creates a Doppler shift that must be tracked precisely. A tiny error in predicted frequency can bury the tone under noise, so navigation and communication become the same problem. Yet the link holds, and that persistence becomes part of the meaning. A machine can outlive its designers, and a message can outlast the moment that created it, especially when the message is encoded in physics rather than fashion. The Golden Record frames this as communication across time and unknown recipients. Voyager frames it as communication across distance and unknown physics, where the environment itself becomes the recipient that answers back. Both frames depend on the same premise, that the laws of nature are stable enough to be shared. Hydrogen emits the same frequency, pulsars keep time, and magnetic fields obey consistent rules, whether you are human or something else. If that premise holds, then the record can be decoded and the data can be trusted. If it fails, then the universe is stranger than our messages assume, and even our measurements become parochial. This chapter begins at the far end of the story, because the whisper is the proof of survival. The spacecraft are still there, still moving, still crossing environments no human has visited, and still sending a tone that can be turned into knowledge. From that whisper, we can work backward to the question of what they encountered. We can also work backward to the improbable chain of choices that let them leave at all, because exploration is always part physics and part timing. Voyager was not inevitable, and its trajectory was not routine. A rare alignment of the outer planets opened a path, a once-in-176 years opportunity to visit multiple worlds efficiently, using gravity as a series of stepping stones. That alignment mattered because Jupiter, Saturn, Uranus, and Neptune were positioned so that one flyby could aim the next. In practical terms, it meant a single launch could achieve a grand tour that would otherwise require multiple missions. That alignment turned gravity into fuel, letting a small craft steal momentum from giant planets. It also turned a planetary mission into an escape attempt from the Sun's immediate control, because each assist could add heliocentric speed without burning propellant. A gravity assist is a trade, not a free gift, because momentum is exchanged with the planet's orbit. The planet barely notices, but the spacecraft's trajectory can swing and accelerate dramatically, an elegant hack written into celestial mechanics. The mission designers aim for Jupiter and Saturn, but the math offered more. With the right flybys, a spacecraft could be thrown toward the boundary no one had mapped, and the outward leg could become a new mission without a new launch. So the Golden Record was attached with a clear-eyed humility. It admitted we might never meet the recipient, and that the real audience might be our own future, looking back at what we chose to preserve. It also admitted that the spacecraft might fail before leaving the solar system's influence. The message was a hope, but the engineering was the only way to deliver it, and hope alone cannot hold a pointing lock. That engineering is why the DSN still listens, and why the tones still arrive. It is why we can ask what the sun's bubble looks like from the inside and at the edge, instead of guessing from afar. The documentary's arc follows that outward path, from bright planets to dim boundaries. Each chapter moves farther from familiar light, and closer to the conditions that define our cosmic neighbourhood, where the sun becomes one star among many. We will return to the planetary encounters, because they explain why Voyager mattered to the public. We will then watch the mission become something else, an outward drift into heliophysics, where the headlines are subtle and the stakes are planetary. We will track the heliosphere as a structure, not a metaphor shaped by solar cycles and interstellar pressure. We will define the heliopause as a boundary in fields and particles, not a line, and we will watch how that boundary can ripple. We will ask what it means to be in interstellar space, and why the definition is contested. We will examine what Voyager measured, what it could not measure, and how scientists inferred the rest, because absence of an instrument is not absence of evidence. We will also confront the uncomfortable implication of the data. The sun's protective bubble may be smaller, more porous, and more variable than we assumed, which means our local space weather is connected to the galaxy more directly than we like. That implication reaches back to Earth, because shielding affects radiation environments and long-term habitability. The edge of the heliosphere is not distant trivia, but a boundary condition for life, one that changes as the sun changes. For now, the tones continue, and the antennas keep listening. Two machines whisper from the dark, carrying two messages, one etched in gold and one written in changing plasma, and both are legible only because the link still holds. The messages only matter because the spacecraft survived long enough to deliver them, so we rewind to the beginning, to the alignment that opened the road and the choices that launched Voyager. We rewind from the whisper to the launch window that made the whisper possible, because Voyager's long afterlife begins as a timing problem in celestial mechanics. On screen, the solar system is never still. Planets slide along their tracks like slow sparks, and the camera's now is only a thin slice of a larger clock. Pull back farther, and the stillness vanishes completely, because every orbit is a moving compromise between gravity, inertia, and time. In that clock, the outer planets do not line up like beads on a string. They move in nested, tilted ellipses, each with its own period and its own pace, and each orbit is slightly inclined relative to the others. Even the word orbit hides complexity, because an ellipse has a perihelion and aphelion, and a planet's speed changes as it moves. Kepler's laws make that change inevitable, and they make it predictable in a way that feels almost musical. A planet sweeps equal areas in equal times, which means it moves faster when it's closer to the Sun and slower when it's farther away. That rule is simple to say, yet it produces consequences that ripple outward into mission design. It means the planets are never spaced evenly in time, and the angles between them are always sliding. Jupiter circles the Sun in about 12 years, and its path sets the tempo for many deep space missions. Saturn takes about 29 years, which means it lags behind Jupiter like a second hand that refuses to match the minute hand. Uranus needs 84 years, and Neptune takes 165, so their positions drift with a patience that outlasts careers. In a visualization, their motion can look gentle, almost lazy. But the distances are so large that even slow motion spans billions of kilometers. Because those periods are incommensurate, the geometry between them repeats only after long intervals, and even then it repeats approximately rather than perfectly. The pattern is clockwork, but the clock has many hands, and the hands are not all in the same plane. Orbital precession adds another layer because the ellipses themselves slowly rotate over time under subtle gravitational tugs. Even the reference plane, the ecliptic, only approximates a shared stage because each planet performs on a slightly different tilt. If you could hover above the ecliptic and watch for centuries, you would see near alignments form and dissolve. The planets would sometimes cluster in one broad quadrant of the sky, then slowly spread out again as the years accumulate. The rare moment Voyager needed was not a single straight line. It was a usable sequence of angles arriving in the right order, with enough margin to thread a spacecraft through. In other words, the mission needed a choreography, not a photograph. In the late 20th century, those hands approached a rare configuration. Jupiter, Saturn, Uranus, and Neptune arranged so one flyby could aim the next, and the chain could continue without requiring impossible fuel. The opportunity was not mystical, and it was not perfect alignment in a single line. It was a corridor of angles that made sequential assists feasible, like a set of open gates that would not stay open. On screen, you can imagine the corridor as a moving tunnel in space, wide enough for a well-aimed craft, narrow enough to punish hesitation. Mission planners called it the Grand Tour, a phrase that sounded romantic but disguised a severe engineering constraint. The math was the real story, and the story had a deadline. Behind the scenes, ephemerides, tables of planetary positions refined by decades of observations, were becoming accurate enough to support an interplanetary relay race. This was not just astronomy in the abstract, but astronomy as infrastructure, built from observatories, radar ranging, and careful bookkeeping. A rocket in the 1970s could reach Jupiter, and that alone was already a triumph of navigation and propulsion. Reaching Saturn was possible with careful design, but it demanded that Jupiter be used as more than a destination. Reaching Uranus and Neptune on one mission was otherwise unrealistic, because the energy required would exceed what any practical launch vehicle could provide. Even if you could imagine a larger booster, you would still face the tyranny of mass, because every kilogram of propellant must itself be accelerated, the limitation was not imagination, but energy. And energy in spaceflight is often expressed as delta V. Delta V is not a speed you travel at, but a budget of velocity change you can purchase with fuel. For deep missions, the rocket equation becomes unforgiving, because it ties performance to an exponential curve. Each extra meter per second demands exponentially more propellant, which demands a larger tank, which demands more propellant again. That feedback loop is why clever trajectories matter as much as powerful engines. To visit multiple outer planets with propulsive burns, the required fuel mass would explode beyond any launch vehicle, and the spacecraft would become mostly tank. Even if you could lift it, you would still have to carry that propellant for years, protecting it from leaks, temperature swings, and the slow entropy of time. Long cruises also punish complexity, because valves stick, seals age, and sensors drift. The Grand Tour therefore had to be elegant, not merely ambitious. Gravity assists changed the accounting. They turned planetary motion into a resource, and they let trajectory replace propellant, which is why the alignment mattered so much. Instead of paying for every course change with fuel, you could borrow the momentum of a planet that was already moving at tens of kilometers per second around the Sun. The planet's orbit becomes a kind of bank account, and the spacecraft makes a withdrawal so small the ledger barely notices. A gravity assist is a momentum trade with a moving planet, and the trade is negotiated by geometry. The spacecraft leaves with a different speed and direction relative to the Sun, and that difference can be dramatic even when the spacecraft never fires its engine. The encounter is brief, but the consequences are long-lived, because the new heliocentric trajectory persists for years. What looks like a simple bend on a diagram is actually a reallocation of energy between frames of reference. In the planet's frame, the spacecraft falls in and climbs out with nearly the same speed, because gravity is conservative. The planet's gravity bends the path like a curved mirror, redirecting the velocity vector without permanently changing the spacecraft's speed relative to the planet. The path is a hyperbola, not an orbit, because the spacecraft is not captured. It enters, swings and leaves, carrying away a new direction like a compass needle snapped into place. In the Sun's frame, the planet is not stationary, and that is where the magic becomes physics. The spacecraft can steal a tiny slice of the planet's orbital energy and carry it away, leaving the planet with an equally tiny loss. The planet pays the bill by slowing an immeasurably small amount, and the spacecraft receives a measurable boost because it is so light. Conservation laws stay intact, nothing is created, yet the bookkeeping depends on which frame you choose to watch. The honest intuition is a moving walkway. Step onto it at the right angle, and your speed relative to the building changes without your legs working harder, because the walkway is already carrying momentum. Another intuition is a slingshot around a runner. If you swing behind the runner, you can leave with some of the runner's forward motion, and the runner hardly notices the exchange. The key, in both cases, is timing and approach angle, because the gift only appears if you meet the motion correctly. The physics is not free energy, and it is not cheating. It is conservation of momentum applied to a three-body geometry that favours the small object, and it works only because the planet is already in motion. The spacecraft's path is a hyperbola relative to the planet, and the key parameter is the turning angle, which depends on how close you dare to pass. That turning angle also depends on the planet's mass and the spacecraft's incoming speed, which means Jupiter is a far more powerful lever than Uranus. That dare is not rhetorical. Closer passes produce larger deflections, but they also increase risk. Radiation belts, ring particles, uncertain moon environments, and gravity fields that are never perfectly known. Every kilometre of altitude is a negotiation between science, safety, and the trajectory that must follow. On screen, the aim point is a dot, but in mission rooms it becomes a debate that can last months. This trick had been used before, but never at this scale. Mariner 10 had used Venus to reach Mercury, proving the method in practice, and Pioneer missions had shown that Jupiter could be approached and survived. Those earlier successes mattered politically as well as technically, because they made gravity assist feel like a tool rather than a gamble. The Grand Tour used Jupiter as the first engine, then Saturn as the second, and it treated the outer solar system like a connected system rather than isolated targets. After Saturn, the path could fork, and that fork mattered more than the public realised. One branch aimed for Uranus and Neptune, continuing the tour as the alignment allowed. Another branch aimed for a faster exit from the solar system, sacrificing later planets to gain time on the outward run. The fork was not a dramatic mid-course choice made on a whim. It was encoded in the Saturn flyby geometry, in the altitude, and in which side of the planet the spacecraft passed. That fork shaped the mission architecture, and it also shaped the numbering that still confuses people. Voyager 2 launched first because its route needed the earlier departure, and the geometry would not wait. Its trajectory was longer in time because it would visit more worlds, and each additional encounter imposed constraints on the next. Every flyby is both an arrival and a departure, which means every success locks in the next obligation. Voyager 1 launched later, but on a faster path. It would reach Jupiter and Saturn first, then leave on a steeper outbound line, and that steepness was not just a dramatic angle on a diagram. It was a higher heliocentric speed, purchased by choosing a different Saturn flyby geometry. That choice prioritized Titan, because Titan's gravity and Saturn's position could shape the exit corridor in a way that protected the science goals. The names followed launch order, not arrival order, which is why the record book reads backward. Voyager 1 became the first to Jupiter, the first to Saturn, and later the first to the heliopause, even though it was the second vehicle to leave Earth. The numbering is a reminder that a mission is a sequence of decisions, not a single moment of ignition. It also hints at the strange way time works in deep space, where first is often a property of geometry rather than effort. These choices were not just about sightseeing. They were about turning a planetary mission into a long baseline experiment across the Sun's domain, and they were made in an era when interstellar missions still sounded like speculative fiction. Each assist did two things at once. It delivered a close flyby, and it set the spacecraft's heliocentric speed for the decades that followed, locking in the rate at which it would eat through distance. In that sense, the planets were not only targets, they were launch ramps built by nature. The Grand Tour window was brief in practical terms. Miss it and the next comparable corridor would not return for roughly 176 years, which is long enough to turn planning into history. That number is not a magic cycle, and it is not exact to the day. It is a useful way to express how rarely the geometry becomes this favourable, given the outer planet's different periods and the mission's specific requirements. It is also a reminder that the solar system offers opportunities on its own schedule, not ours. The deeper point is that orbital dynamics creates opportunities with expiration dates. Exploration depends on those dates as much as on budgets, and sometimes more than on politics. When the window opens, it does not care whether your spacecraft is ready, whether your funding is secure, or whether your team has slept. The planets keep time with indifferent precision, and that indifference becomes a kind of pressure. Once the window opened, the mission became a high-wire act. Gravity assists amplify small errors, because the next target depends on the last bend, and because the line of flight is set long before you see the planet as anything but a bright point. A flyby is not a pass-by in the casual sense. It is a precisely timed fall through a planet's gravity well, with a departure vector chosen in advance, and with limited opportunities to correct mistakes. The spacecraft must arrive at the right place and time, often within minutes, because the planet is moving and the aim point is a point in space that will not wait. It must pass at the right altitude, often within tens of kilometers, because the turning angle and the science both depend on that distance. On a visualization, the miss distance looks like a hairline. In reality, it is an invisible corridor in a vacuum, defined only by calculations and radio data. At Jupiter, the speed is enormous. The encounter is over in hours, and the geometry is set by decisions made months earlier, when Jupiter was still far away and the spacecraft was still adjusting its cruise. Jupiter's gravity is so strong that it can reshape a trajectory quickly, and its magnetosphere is so intense that it can reshape instruments if you are careless. On screen, Jupiter swells from a star to a world in days, then slides past in a rush of cloud bands and shadowed moons. At Saturn, the stakes multiply. A small miss in the aim point can change the ring plane crossing, the moon flybys, and the exit direction, and Saturn's system adds its own hazards. Rings are not solid bands. They are countless particles, from dust to boulders, and even a small grain at tens of kilometers per second is a bullet. The ring plane is also a measurement opportunity, because it is a natural laboratory for collisions, resonances, and wave patterns carved by moons. The navigation problem is solved with radio and patience, and the solution is never a single measurement. Engineers measure Doppler shifts and ranging tones, then estimate the trajectory in a noisy universe. using models that must account for both known physics and stubborn uncertainties. The Deep Space Network becomes the mission's nervous system, giant antennas listening for a carrier signal so faint it can be buried in thermal noise. On screen, the dishes pivot slowly under a hard blue sky, as if they're trying to hear a whisper through a storm. The spacecraft is tracked as a point mass, but it is pushed by subtle forces, and subtle forces become decisive over years. Solar radiation pressure is small, yet photons carry momentum, and the spacecraft presents an area that catches that push. Thruster leaks can add a steady bias, and outgassing from materials can produce tiny jets when temperatures change. Even the heat emitted from onboard power systems can create a minuscule recoil, a reminder that nothing in physics is truly just waste. Trajectory correction maneuvers are the only way to trim the path. They are short burns, planned carefully, executed with limited fuel and no redo, and they must be done while the spacecraft is far beyond any possibility of repair. The burns must be placed at the right time. A small correction early can save a large correction later, because errors grow with distance and because geometry magnifies angular mistakes. In mission terms, that is leverage. Spend a little now or pay dearly later. The required precision is hard to grasp at interplanetary scales. A fraction of a degree near Earth becomes millions of kilometers by the time you reach Saturn, and the spacecraft's target is not the planet itself, but a specific point relative to it. At billions of kilometers, the tolerances become cruel. A tiny angular error can mean missing a planet entirely, or passing too far for useful science, or leaving on an outbound path that cannot be fixed. The cruelty is mathematical, not emotional, yet it feels personal when you have only one chance. The spacecraft cannot be steered like an airplane. Commands take tens of minutes to arrive, and the craft must execute them autonomously, because by the time you see a problem on Earth, it is already in the past. That autonomy is limited by 1970s computing. The system is reliable, but it is not flexible, and it cannot improvise new plans in real time, which means the plan must anticipate failure modes. In practice, this turns operations into choreography, where each step is rehearsed on Earth with simulators and checklists. So the mission is built around prediction. Teams model the gravity field, the ephemerids, and the spacecraft's state, then commit to a sequence, and they do it with a seriousness that borders on ritual. Gravity fields are not perfectly spherical. Jupiter and Saturn are oblate, their mass distributions shaped by rapid rotation, and their moons tug at the field in ways that must be accounted for. Even small harmonics in the gravity model can nudge a trajectory, and those nudges accumulate across an encounter. The tension in this chapter is not only the rarity of the alignment, it is the fact that the alignment demands perfection at each step, because each step is both a destination and a launch. Jupiter's role is both gift and threat. Its gravity can add speed, but it can also fling the spacecraft into a useless orbit if the aim is wrong, or dive it into radiation that instruments cannot endure. The planet's radiation belts are shaped by its magnetic field, and that field traps charged particles like a vast invisible storm. The same is true at Saturn, where the geometry determines everything that follows. After Saturn, the mission either becomes a tour or an escape, and that choice is embedded in a single flyby altitude and a single timing. Voyager 2's path used Saturn to reach Uranus. Uranus then became the next moving platform, bending the trajectory toward Neptune, and each planet in that chain acted like a relay runner handing off speed. The handoff is not gentle, it is a precise exchange, where arriving a few minutes early or late can change the baton's direction. Neptune was the last planned planetary assist. After Neptune, the spacecraft would be thrown outward, no longer chasing planets, only distance, and the camera would eventually see nothing but stars. Voyager 1's path used Saturn differently. It prioritized Titan and a faster outbound trajectory, even though that choice ended its planetary tour, because Titan's gravity and Saturn's geometry could shape the exit speed in a way no engine could match. In the mission's logic, Titan was both a scientific prize and a steering wheel. The trade was explicit. More targets meant a slower exit. A faster exit meant fewer targets, but a quicker approach to the sun's boundary, and the boundary was becoming the quiet obsession behind the spectacle. This is where the planetary story connects to cosmology, not as a leap to distant galaxies, but as a disciplined extension of local physics. The goal was not only to see worlds, but to use worlds as engines, and to use the resulting trajectory as a probe of space itself. The engines were not chemical and not nuclear. They were gravitational, and they converted orbital motion into a probe's outward kinetic energy, which is simply the energy of motion relative to the Sun. That outward energy matters because the heliosphere is vast. If you want to measure its edge within a human lifetime, you must leave quickly, and you must keep leaving even when the planets are gone. Speed is not drama here. Speed is access. Cosmology begins locally, with fields and particles. The solar system is a laboratory where a star's wind meets the galaxy's pressure, and where a magnetic bubble confronts a larger magnetic sea. The heliosphere is inflated by the solar wind and shaped by the interstellar medium. Its boundary is a balance of plasma pressure, magnetic pressure, and flow, and those pressures change with the solar cycle like a slow pulse. When the Sun is more active, the bubble can swell. When it quiets, the bubble can relax, and the boundary shifts like a shoreline. To picture it, imagine the Sun breathing outward, exhaling charged particles and magnetic field lines that spiral with the Sun's rotation. That spiral, the Parker spiral, means the magnetic field is not a simple radial line. It is a wound structure, and it carries turbulence, shocks, and discontinuities that evolve with time. Far from the Sun, those structures can merge and steepen, forming broad interaction regions that sweep outward like weather fronts. Voyager's trajectory turns that boundary into an addressable destination. It creates a line through space along which conditions can be sampled for decades, and it does so from two different directions that will later become crucial. To make that sampling meaningful, the spacecraft must carry the right tools. The instrument suite is the mission's vocabulary, and it foreshadows the later chapters, when images fade and numbers become the narrative. The imaging system records reflected sunlight and structure. It makes the planets legible, but it also teaches the team how to operate at distance, how to plan exposures, and how to compress and transmit pictures through a narrow radio link. On screen, this is the bright part of the mission: banded Jupiter, the thin rings of Saturn, moons lit like stones in a spotlight. The images are also engineering proof, because every frame confirms pointing accuracy, timing, and the health of a fragile optical chain. Infrared and ultraviolet spectrometers measure composition and temperature. They translate light into chemistry, and they hint at processes that are otherwise invisible, because molecules absorb and emit at specific wavelengths. A spectrum is a fingerprint, and the spacecraft carries the ability to read those fingerprints in a place where laboratories cannot go. In practice, this means detecting methane bands, haze layers, and auroral emissions, then turning those patterns into models of atmospheres and energy flow. Magnetometers measure the direction and strength of magnetic fields. They will later become the primary witnesses when the solar magnetic domain ends, but even early on they reveal how planets carve cavities in the solar wind. The instruments sit on long booms to reduce interference from the spacecraft itself, because even a small onboard magnetic field can contaminate a delicate measurement. On screen, the boom is a thin line against blackness, an antenna for an invisible architecture. Plasma instruments measure the solar wind speed, density, and temperature when they can. They will later define shocks, slowdowns, and transitions in the outer heliosphere, where the solar wind begins to lose its dominance. Plasma is just ionized gas in plain language, but it behaves like a fluid tied to magnetic fields, and that coupling creates structures that can be measured only in situ. When the flow changes, it is not merely a number, it is a clue about pressure, turbulence, and the shape of the boundary ahead. Particle detectors count energetic ions and electrons. They separate populations that come from the Sun from those that come from beyond, and they do it by measuring energy, charge, and arrival direction. Some particles are accelerated at shocks driven by solar eruptions. Others are born in the boundary region itself, where neutral atoms become ions and are picked up by the solar wind. Those pickup ions matter because they carry information from interstellar neutrals that drift into the heliosphere unnoticed until they are ionized. Cosmic ray detectors measure the highest energy particles that penetrate the heliosphere. They will later show how shielding changes as the spacecraft approaches interstellar space, because the heliosphere acts like a modulating filter. When the Sun's influence weakens, the background of galactic cosmic rays rises, and the spacecraft becomes a counter-clicking in the dark. The rise is not instantaneous. It is a gradient, and the shape of that gradient tells you whether the boundary is sharp, layered, or porous. Taken together, these instruments are not just for planetary science. They are a distributed sensor package moving through a changing medium, and the medium is the Sun's extended atmosphere. The Grand Tour therefore has a second purpose, even if it is not the headline. It is the creation of a long-lived probe that can map the Sun's influence, not with a single snapshot but with a long transect. The mapping is not done with pictures. It is done with gradients in particle flux, shifts in magnetic orientation, and changes in plasma behavior, and those changes often arrive as slow trends rather than dramatic events. The outward journey becomes a baseline measurement. Every additional astronomical unit adds another data point in a profile of the heliosphere, and the profile is built patiently, like a climate record. The patience is scientific discipline, because the outer solar system does not reward impatience. That profile is essential to the central question. If the Sun's domain has an edge, then its size and structure must be measured, not assumed, and measurement requires persistence. Where does the solar wind slow to subsonic speeds? Where does it become turbulent? Where does the magnetic field change character, and how sharp is the transition? Another question hangs behind those questions. Is the boundary a clean border, or a region of mixing where solar and interstellar are not clean labels? The mission's early design did not guarantee interstellar science. It created the possibility, and then it depended on survival and continued communication, which were not trivial assumptions. Still, the alignment forced a decision that could not be postponed. Either you launch in the window or you accept that the experiment ends before it begins, because the planets will not return to these angles on any useful schedule. That urgency shaped not only trajectories but schedules, testing, and the willingness to accept risk. The window also forced a philosophical commitment. You had to believe that a machine could operate long enough for the payoff to arrive, and you had to believe that the people who launched it would not be the only ones to interpret its data. In the 1970s, that belief was not obvious. Electronics aged quickly, software was limited, and deep space operations were still a young craft, learned through a handful of missions and hard-earned mistakes. There is a quiet humility in that era's engineering, because it assumes failure is normal and designs around it anyway. Yet the trajectory demanded patience. Even with assists, the boundary with interstellar space lay far beyond Neptune, far beyond any previous mission, and far beyond the point where sunlight is anything but a dim star. The spacecraft would spend years in cruise, then decades in darkness. The science return would shift from spectacular images to subtle cumulative measurements, and the public attention would have to shift with it, or not shift at all. What does it mean to build a mission whose climax may arrive after the original team has retired? This is why the Grand Tour is more than a travel plan. It is a bet that time can be turned into data, if the path is right, and if the craft remains coherent. It is also a bet that a long experiment can remain meaningful as theories evolve, because the heliosphere is not static, and the galaxy does not hold still. The craft becomes a messenger not only from far away, but from far into the future of its own design assumptions. The high wire act continued after the last planet. The spacecraft had to be aimed not at a target, but at a future region of space, and that is a different kind of navigation. A planet is a visible object with a known gravity well. A boundary is an inference, a set of physical conditions that must be detected as they change. The mission therefore shifts from hitting a bullseye to reading a landscape that cannot be photographed. That region was defined by theory and inference. It was where the solar wind would slow, where the magnetic field would compress, and where interstellar particles would intrude, and each of those expectations carried uncertainty. The mission did not know the exact distance. It only knew the direction and the need to keep moving outward with enough speed, because speed is what makes a distant boundary reachable. In a sense, the alignment did not merely enable visits, it purchased decades. Gravity assists provided that speed, and they also set the spacecraft on trajectories that would diverge, giving two different cuts through the heliosphere. Those two cuts would matter later. Different latitudes, different longitudes, different solar cycle timing, and different interstellar conditions along each path, which means the two Voyagers would not simply repeat each other's results. They would argue with each other in data, and the argument would be informative. So the Grand Tour is also an experimental design. Two probes, two trajectories, and decades of separation create a comparative dataset, and comparison is how you tell structure from coincidence. If one probe sees a feature and the other does not, the difference becomes a clue rather than a failure. Is the heliosphere symmetric, or is it distorted by the galaxy's magnetic field and the sun's motion through the local interstellar medium? The dataset is messy, because instruments fail and power declines, and because the environment itself changes with solar activity, it is still priceless because nothing else samples the boundary directly, and because remote sensing cannot easily measure magnetic fields and plasma conditions at those distances. The messiness is part of the truth, because nature is not a controlled laboratory. The mission becomes a long conversation with noise, drift, and rare events. As the spacecraft left the planets behind, the mission's centre of gravity shifted. The public saw the last images, but the instruments kept counting, and the radio carrier kept arriving at Earth as a thin tone in the Deep Space Network's receivers. The story becomes quieter, and the stakes become larger. The question moves from what is out there to where our home ends, and whether that end is a wall or a gradient. On screen, the visuals simplify. Fewer worlds, more darkness. Yet the graphs and numbers grow more charged with meaning. The alignment that enabled the tour also enabled the escape. A limited rocket became an interplanetary mission, then an interstellar mission in practice, and the transformation happened not through new engines but through a rare geometry. That transformation is the core beat of this chapter. Celestial mechanics opened a door and gravity assists pushed two machines through it, and the machines kept going long after the applause faded. Now the door is closed behind them. The planets have moved on, and the corridor has dissolved back into ordinary geometry, and no one can reopen it on demand. What remains is the outbound drift and the long measurement. The solar system becomes a breathing island, and Voyager becomes the gauge at its edge, listening to fields and particles where the sun's influence thins. In the dark beyond the last planet, the spacecraft's motion is almost pure inertia, an old promise kept by momentum. The window was brief, but the craft needed to endure. So we turn from trajectory to survival and ask how 1970s machines learned deep time. The window was brief, but the craft needed to endure. Voyager's interstellar story begins as an engineering wager against deep time, made in conference rooms and clean rooms long before anyone knew what Interstellar would demand. In those early meetings, endurance was not a slogan, it was a requirement, because the spacecraft would be alone, and aloneness is a harsh design environment. In the 1970s, the mission was sold as a few years of planetary science, a grand tour made possible by rare planetary alignment. That alignment, first recognized in the 1960s, offered a once-in-176 years chance to hop between outer planets using gravity assists. The public story leaned on flybys and photographs, yet the internal logic quietly assumed something longer, because distance punishes every optimistic estimate. If a component lasts a few years on paper, what does it do after 10 or 20 when the margins are gone? Even the launch era matters here, because the baseline technology set the rules of survival. Electronics were bulky, memory was scarce, and radiation-hardened parts were limited compared with what later decades would offer. Spaceflight still carried the lessons of early probes that failed quickly, often for mundane reasons like stuck valves or drifting oscillators. Voyager's designers were not chasing elegance, they were chasing survivability, because in deep space, maintenance is a fantasy, and replacement is a myth. Survival in deep space is not one problem, and it never arrives as a single dramatic test. It is power, heat, pointing, computing, and communication. Each one degrading, each one demanding trade-offs, and each one capable of ending the mission without warning. The craft is a balancing act performed over decades, where small degradations accumulate until they become operational constraints. The mystery is not that something breaks, but that so much continues to work. At the centre sits a nuclear heartbeat, steady at first and then inevitably fading. Voyager does not run on sunlight, because sunlight becomes irrelevant beyond the giants, where the solar constant collapses and the panels that power near-Earth spacecraft become dead weight. Solar intensity falls with the inverse square of distance, so at Jupiter it is already a fraction of Earth's, and beyond that it dwindles into engineering insignificance. In that dimming, the mission's power system becomes its true clock. Each spacecraft carries radioisotope thermoelectric generators, RTGs, bolted like heavy lanterns to a long boom. In archival footage, they look almost casual, cylinders with fins, yet their placement is deliberate, keeping heat and radiation away from sensitive instruments. The boom is a compromise between safety and structure, long enough to reduce interference but rigid enough to survive launch vibration. In cleanroom visuals, technicians move around them with careful choreography, as if approaching a quiet furnace. They do not produce electricity directly from radiation, but from heat. That distinction matters because the generator is essentially a controlled thermal gradient machine, turning steady warmth into steady voltage with no moving parts to wear. It is not a reactor, and it is not a battery, and the simplicity is the point. No spinning turbines, no chemical depletion, no mechanical timing chain waiting to snap. Inside the RTG, plutonium-238 decays and releases energy as thermal power. The isotope's half-life is about 87.7 years, which sets the mission's long slope, a statistical clock that keeps ticking whether Voyager is healthy or not. Half-life does not mean the power vanishes suddenly. It means the decline is smooth and relentless, like a dimmer turned down by physics. That slow decline is predictable enough to plan around, yet unforgiving enough to dominate every long-term decision. Plutonium-238 is chosen for a reason that sounds almost poetic in engineering terms. It produces abundant heat per unit mass. It emits primarily alpha particles that are easier to shield, and it can deliver predictable output without the volatility of a chain reaction. Alpha particles are stopped by relatively modest shielding, but the heat cannot be stopped at all, because heat is the product you are buying. In the background sits a history of nuclear materials work, where the isotope had to be produced, handled, and certified for launch safety. That decay is predictable, and the power curve is a slow countdown. Every year the heat output drops, and the electrical output drops faster, because thermoelectric conversion efficiency also changes as temperatures drift and materials age. The hot junction cools slightly as the source weakens, and the cold junction changes as the spacecraft's thermal balance evolves. Even wiring resistance and contact quality matter, because at low power, every fractional loss becomes operationally visible. Thermocouples convert a temperature difference into voltage through the Seebeck effect. The hot side is the plutonium heat source, and the cold side is deep space, which is not cold air, but a vacuum that only accepts heat through radiation. That makes the cold side a strange sink, because it is not about temperature alone. It is about how efficiently surfaces can radiate energy away. The RTG's fins, coatings, and geometry are part of the electrical design, because they shape the thermal gradient that makes electricity possible. In visuals, you can imagine the RTG as a tiny furnace surrounded by fins, glowing only in infrared. Heat flows outward, and the thermoelectric junctions skim a fraction of that flow, converting it into a trickle of electrical current. The rest becomes waste heat, spilling into space and into the spacecraft's thermal architecture. In a shot that lingers, the RTG's waste looks like a resource, because it is. The conversion is simple and inefficient, which is exactly why it lasts. No moving parts means no bearings to seize, no pumps to fail, and no lubricants to evaporate or polymerize after years of radiation. The materials still age, and junctions still drift, but the failure modes are slow rather than catastrophic. In deep time, slow failure is survivable, because it gives engineers room to adapt. Early on, the RTGs provide enough electricity to run instruments, heaters, transmitters, and computers with margin. That margin is a kind of hidden fuel, spent in small amounts every day without anyone noticing. Decades later, power management becomes the mission's central drama, because the spacecraft is still alive but the budget is no longer generous. A system designed for exploration becomes a system designed for triage, and the difference is measured in watts. The spacecraft does not die from distance. It dies from watts, because every subsystem is a load competing for a shrinking budget, and a few missing watts can cascade into colder temperatures, noisier electronics, and weaker communications. Power shortfalls are rarely isolated because heat and power are coupled, and both affect pointing and signal quality. When the budget tightens, the spacecraft becomes more sensitive to small disturbances, as if age has sharpened every edge. Engineers treat power like oxygen on a long voyage. They schedule activities, switch off heaters, and accept that some instruments must go dark forever, not because the sensors are broken, but because the spacecraft can no longer afford them. The language becomes careful and almost domestic. What can be turned off? What must stay warm? What can be woken only briefly? Each decision is reversible in theory, yet irreversible in practice, because every restart carries risk. This is how Voyager sheds capabilities without losing identity. The probe becomes less like a camera platform and more like a minimal scientific outpost, a stable carrier for a handful of measurements that still matter at the edge. The mission's personality changes, from spectacular imagery to quiet diagnostics of fields and particles. It is a shift from seeing to sensing, and from pictures to physics. The logic is conservative design, built around what cannot be fixed. Components are chosen for stability, tested for extremes, and operated with wide margins, because a margin is a form of time stored in advance. In spacecraft engineering, margin is not pessimism, it is respect for the unknown. It is the admission that the environment will find every weakness, and it will do so patiently. In the lab, tested for extremes means more than a checklist. Hardware is baked, frozen, shaken, and exposed to vacuum, while engineers watch for tiny drifts that could become fatal when the craft is light hours away. Thermal cycling reveals solder fatigue, vibration reveals loose connectors, and vacuum reveals outgassing that can fog optics or alter insulation performance. The tests are meant to be cruel because space will be cruel for longer. Redundancy is the next pillar, because single-point failures are unacceptable when repair is impossible. Voyager carries duplicated systems for critical functions, and the craft can switch sides, as if it has two nervous systems waiting in parallel. Redundancy is also a psychological design choice, because it gives the ground team options when something behaves oddly. An option is not a guarantee, but it is a path forward. There are redundant receivers, transmitters, and command decoders. There are backup attitude sensors and multiple pathways to keep the antenna pointed home, because losing Earth pointing is not a setback, it is an ending. Even a healthy spacecraft becomes useless if it cannot be commanded or heard. In the cold emptiness, communication is the only proof of life. Redundancy is not free. It adds mass, complexity, and power draw, so the mission chooses it carefully, protecting the functions that keep Voyager alive while allowing less essential systems to be singular and therefore expendable. This is a philosophy of prioritization, written into the hardware before the first launch bolt is tightened. It assumes that sacrifice will be necessary, and it decides in advance what can be sacrificed. Fault protection is not intelligence in the modern sense. It is a small set of rules that detect dangerous states and retreat to safety, like a reflex rather than a thought, designed to be reliable under stress. These rules are intentionally limited, because a complicated safety system can fail in complicated ways. In a mission with hours of delay, a simple reflex can be the difference between survival and silence. If the spacecraft senses a problem, it can enter safe mode. Safe mode reduces activity, stabilizes attitude, and preserves the radio link, because the first priority is always to remain reachable by the people who can diagnose it. The spacecraft becomes conservative, almost motionless, and it waits. In that waiting is an implicit trust that Earth will still be listening. A safe mode event is dramatic precisely because it is quiet. Instruments stop, the spacecraft simplifies itself, and on Earth the first clue is often a change in tone, a different pattern in a carrier signal arriving from the dark. The DSN operators see it as a subtle shift in telemetry frames, a different heartbeat in the data. Then the long process begins: interpretation, hypothesis, command sequences, and more waiting. The computers are minimal by modern standards, with tiny memory and limited instruction sets. That simplicity reduces complexity, and complexity is where hidden failures breed, especially when software must survive decades of changing operational needs. The limitations are stark: memory measured in kilobytes, processing that would feel slow even in a museum exhibit. Yet those constraints also force discipline, and discipline is a kind of reliability. Voyager's onboard computers were built for determinism. They execute known sequences, store limited state, and avoid elaborate abstractions because every additional layer is another place for a rare bug to hide. The code is closer to procedure than to improvisation, and that is intentional. When a spacecraft is billions of kilometers away, you want it to behave like a metronome, not like a conversation. Voyager's software is not designed to be elegant. It is designed to be predictable, because predictability lets engineers reason across decades, even as team members retire, and documentation becomes a kind of archaeological record. Procedures become rituals, and rituals become safety, because they reduce the chance of human error. The mission's continuity depends on institutional memory, carefully preserved in notes, diagrams, and inherited habits. The spacecraft is a network of subsystems that must cooperate under delay. Commands take hours to arrive, so autonomy must cover the gaps, and the craft must handle small emergencies without waiting for permission. Even routine operations are shaped by that delay, because there is no real-time steering, only careful planning. The spacecraft is always living slightly ahead of the people who control it. Even with autonomy, the ground remains part of the machine. The mission is a distributed system, split between a probe in darkness and a planet that listens, where human judgment becomes a subsystem with its own limits. Fatigue, scheduling, and interpretation become engineering variables, even if they never appear on a schematic. The spacecraft's endurance is matched by the endurance of the people who keep showing up. Thermal survival is the quieter miracle, because electronics hate cold. Far from the sun, the environment is a near-perfect heat sink, and anything warm wants to radiate away its energy into a sky that never warms back. In vacuum, there is no convective blanket, only radiation and conduction through structure. The spacecraft's warmth is always trying to escape, and the design is a constant attempt to slow that escape. Voyager's heat does not come from sunlight. It comes from waste heat, mostly from the RTGs, and that waste becomes a life support system, warming cavities and circuit boards that would otherwise drop below their rated temperatures. The craft effectively lives off its own inefficiency, turning lost energy into survival. When power declines, that same inefficiency declines too, and the thermal problem tightens like a noose. In thermal diagrams, the spacecraft looks like a small city of compartments. Boxes share walls, harnesses conduct heat, and the placement of components becomes a form of architecture, designed so warmth migrates where it is needed. Engineers think in heat paths the way architects think in hallways, because heat must be guided. A warm oscillator here can protect a cold sensor there, if the structure is arranged wisely. The spacecraft is wrapped in insulation to slow heat loss. Internal compartments are arranged to share warmth, because every heater costs power, and power is already being rationed like food on a winter expedition. The insulation is not a single layer, but a strategy, tuned to different surfaces and different exposure angles. In the outer dark, those choices become visible in telemetry temperatures, like a map of survival. Multi-layer insulation, those crinkled blankets seen in cleanroom shots, is more than visual iconography. It reduces radiative exchange, trapping heat in layers, and it helps the craft behave less like bare metal and more like a thermos. The layers create many small gaps, and those gaps interrupt heat transfer in a vacuum-friendly way. In close-up visuals, the blanket looks fragile, yet it is one of the mission's strongest defenses. Louvers regulate temperature by opening and closing to radiate heat when needed. They are passive mechanisms tuned for a range of conditions, and they embody a philosophy of reliability. Let physics do the work when possible. A bimetallic spring can respond to temperature without software, without commands, and without power. In a mission measured in decades, passive control is a form of humility. In the inner mission, louvers prevent overheating near the sun and during heavy operations. In the outer mission, they become less active as the craft fights freezing, because there is less excess heat to shed. Their behavior becomes part of the spacecraft's seasonal rhythm, even though there are no seasons in deep space. The craft's weather is created by distance and by dwindling energy. As power falls, heaters are turned off one by one, components drift toward their survival limits, and engineers learn which margins were real, because the only true test of a design is time spent in the environment. Telemetry becomes a kind of medical chart, watched for fevers and chills. A few degrees can separate stable operation from unpredictable behavior, especially in older electronics. Some heaters protect propellant lines, others protect oscillators and electronics whose frequency stability depends on temperature. Turning one off can save watts today, yet it may also invite a failure months later, when a cold-soaked component behaves differently. The risk is not always immediate, and that delay makes the decisions harder. When the spacecraft is far away, consequences arrive slowly, like distant thunder. Thermal constraints mirror a physical truth about the solar system. Energy, warmth, and sunlight fade with distance, and the spacecraft must live that gradient, translating astronomical geometry into operational hardship. The numbers are simple, but the consequences are complex because every subsystem depends on temperature. In the outer dark, thermodynamics becomes mission planning. The farther Voyager travels, the more it resembles a small island of heat in an ocean of cold. Its engineering becomes a model of how environments impose physics, and how physics, in turn, shapes the very questions a mission can still ask. What does it mean to explore when exploration itself consumes the warmth that keeps you alive? The mystery deepens because survival and curiosity draw from the same diminishing source. Pointing is another survival requirement, because the high-gain antenna must face Earth. A mispointed antenna turns a whisper into silence, and silence is the one condition that cannot be debugged from the ground. The antenna beam is narrow, and at interstellar distances a tiny angular error can miss Earth entirely. In that geometry, attitude control is not just navigation, it is communication. The high-gain antenna is a rigid dish, and it does not search for Earth. The spacecraft must orient its entire body, keeping the dish aligned while also managing thermal balance and instrument pointing constraints. That creates a constant negotiation between what the spacecraft must face and what it must avoid. In visuals, the dish becomes a single eye, always turned toward a pale star that is really home. Attitude control uses hydrazine thrusters because reaction wheels would saturate and fail over long timescales. Hydrazine is finite, and every correction spends it, turning orientation into a consumable resource. The fuel is not just for dramatic maneuvers, it is for the daily work of staying pointed. Over decades, even tiny pulses add up, and the tank becomes a countdown hidden inside the spacecraft. Small thruster pulses counter slow drifts and keep the antenna aligned. Over decades, thruster wear, valve behavior, and propellant management become critical, because a tiny leak or a sticky valve can rewrite the mission's remaining years. Thrusters are simple devices, yet they live hard lives, opening and closing thousands of times in the cold. Each pulse is a decision, and each decision leaves a trace in the fuel budget. Hydrazine thrusters also introduce subtle side effects. Each pulse imparts a small torque and a small translation, and over long periods those nudges must be accounted for, especially when Doppler tracking is sensitive to minute velocity changes. The spacecraft's motion becomes a blend of celestial mechanics and housekeeping. Even keeping still requires thrust, and thrust leaves fingerprints in the data. Radiation adds a different kind of aging. High-energy particles damage electronics, flip bits, and degrade sensors, and the risk accumulates silently, like weathering that never stops because there is no shelter in interplanetary space. Some particles come from the Sun, some from distant supernovae, and some from the galaxy's background storms. The spacecraft is a target exposed on all sides, with only modest shielding and careful design to protect it. Jupiter's radiation belts are an early test, but the long cruise is its own exposure. Cosmic rays and solar events slowly change the hardware, altering semiconductor properties and increasing the chance that a single particle can upset a memory state. A bit flip can be corrected, but repeated damage can change thresholds and noise, making components less forgiving. The aging is invisible until it is suddenly operational. Some failures are sudden, like a sensor that stops responding. Others are gradual, like a detector whose calibration drifts until uncertainty grows, forcing scientists to ask whether a trend is real or merely the instrument aging. This is where engineering and science overlap, because interpretation depends on trust in the instrument. When the instrument changes, the meaning of the measurement changes with it. Aging is not only in components, it is in the mission's options, because each workaround consumes something: power, fuel, time, or redundancy. And the act of saving the spacecraft can quietly spend the future. A clever recovery today can reduce flexibility tomorrow, and flexibility is the currency of long missions. The spacecraft survives, but it becomes less able to handle the next surprise. This is why simplicity can be resilience. A system with fewer modes has fewer ways to surprise you, and surprises are expensive at light-hour distances, where even a correct response arrives too late to stop a fast failure. Simplicity also makes diagnosis possible, because engineers can map symptoms to causes without a maze of interactions. In deep space, clarity is a form of protection. Yet Voyager is not simple in the casual sense. It is a carefully bounded complexity, where critical functions have backups and non-critical ones can be sacrificed, and where the remaining machine can still form a coherent scientific voice. The craft is like a ship built with watertight compartments, expecting damage but refusing to sink. Its design assumes loss, then turns loss into a controlled process. The sacrifice is planned, but it still feels like loss. Each instrument shutdown narrows the probe's senses, and each narrowing changes what questions can be asked, because the mission's curiosity must fit inside a shrinking electrical envelope. The shutdowns are often permanent, because restarting can demand power spikes or thermal stability the craft can no longer provide, the laboratory becomes quieter, and the quiet is deliberate. Instruments are turned off to conserve power, starting with those that draw the most or return the least. The sequence is a slow dismantling of a laboratory, performed with the care of surgeons who know they cannot reverse the cut. Engineers watch currents and voltages like vital signs, then make the next cut only when the numbers force it. The spacecraft remains whole, yet its senses become more selective. Cameras, once central, become impossible to justify as the link and power budgets tighten. The mission shifts from images to fields, particles and plasma, where a few numbers per second can still describe an environment no human has ever sampled. The romance changes form, from pictures of worlds to measurements of invisible boundaries. The data becomes abstract, yet the implications become larger. The ultraviolet spectrometer, the infrared system, the plasma instruments, and other packages face the same arithmetic. Keep one alive and another must sleep because the total load must stay below what the RTGs can provide with margin. The choice is rarely about scientific value alone, because thermal needs and operational dependencies complicate the ledger. Sometimes, an instrument is sacrificed because it demands heaters that cannot be spared. This arithmetic is not abstract. Engineers build detailed power profiles, adding up heater loads, transmitter demands, and computer overhead, then comparing the sum to a forecast that declines year after year like a tide going out. The tables become living documents, revised as actual performance deviates from predicted curves. In mission rooms, those numbers carry emotional weight because they translate directly into what can still be asked of the universe. The spacecraft remains functional, but in a more austere form. It becomes a platform for a few key sensors that can still answer the central question, and those sensors must be kept warm, powered, and synchronized with the downlink schedule. Operations become sparse and carefully timed because every hour of activity costs something. The craft is still exploring, but it explores with restraint. That question is not about a planet anymore. It is about the true size of the Sun's domain and the nature of the boundary with interstellar space. A boundary once imagined as a line, but revealed as a region with structure. The heliosphere is not a simple bubble, and the edge is not a wall. It is a layered transition where flows slow, fields twist, and particles change character. To answer it, Voyager must keep talking to Earth. Communication across the void becomes as important as measurement itself, because a perfect instrument is useless if its data cannot cross the expanding gulf. The radio link is the mission's lifeline, and it weakens as surely as the RTGs. The farther the craft goes, the more the mission becomes an exercise in listening. The radio system is modest in power, and the signal spreads as an expanding sphere. Distance turns a transmitter into a near impossible target for receivers, because the same energy must cover an ever-growing area. This is the inverse square law again, now applied to information rather than sunlight. The spacecraft whispers, and the universe dilutes the whisper. As Voyager recedes, the carrier wave arriving at Earth is unimaginably faint. It competes with thermal noise in receivers, with interference, and with the simple fact that the universe itself has a background hiss at radio frequencies. Even the ground equipment generates noise, because any warm electronics produce random motion in electrons. Communication becomes a contest between a deliberate signal and the natural static of matter. This is where the Deep Space Network becomes a quiet third character. Without it, Voyager would be mute long before it reached the edge, and the mission would become a drifting artifact rather than a continuing experiment. The DSN is not just hardware. It is a global practice of precision. It is the Earth learning to hear a spacecraft that is almost lost in the cosmic background. The DSN is a global set of antennas spaced across continents to cover Earth's rotation. It is not one dish, but a choreography of tracking, handoffs and scheduling, where multiple missions compete for the same listening time. Stations in different longitudes pass the signal like a relay, keeping contact as Earth turns. In mission operations, time zones become part of the spacecraft's anatomy. In wide shots, the DSN stations look like white mechanical flowers against desert and mountain. The dishes pivot with slow confidence, following points in the sky that appear empty to the eye, yet are crowded with faint engineered signals. Heat shimmer rises from the ground, while the dish tracks something you cannot see. The visual contrast is striking, massive machinery devoted to catching a whisper. The 70-meter antennas are the heavy lifters for the farthest spacecraft. Their size collects faint energy, and their receivers are tuned for extreme sensitivity, using low-noise amplifiers and carefully controlled electronics to preserve signal integrity. The dish surface must be accurate enough to focus radio waves, and the pointing must be precise enough to stay on target. In the control rooms, the signal appears as a narrow peak, barely lifted above the noise floor. The link budget tightens as distance increases. Delta rates shrink because you trade bandwidth for detectability, and you integrate longer to pull signal from noise, turning communication into a patient act of statistical extraction. Longer integration means fewer bits per second, but more confidence that the bits are real. The mission learns to value reliability over speed, because a slow truth is better than a fast error. What once delivered images can later deliver only a trickle of numbers. The mission adapts by compressing, prioritizing, and accepting gaps, because some measurements must be dropped simply to keep the essential ones flowing. Downlink schedules become carefully planned windows, aligned with DSN availability and spacecraft power constraints. The spacecraft speaks when it can, and Earth listens when it must. Signal travel time becomes part of operations. A command can take many hours to reach Voyager, and the confirmation takes many hours to return, creating a rhythm where decisions are made in the present and verified in the future. That delay is not a metaphor, it is a physical distance expressed in time. In visuals, a simple timeline graphic can show the command leaving Earth, then the long silence, then the reply arriving like an echo. That delay forces a different psychology. Engineers must commit, wait, and then learn what happened long after the moment has passed, which makes every command feel like sending a message into a cave and listening for a distant echo. Caution becomes habit, and habit becomes culture, because you cannot undo a mistake quickly. The mission's pace slows, not from laziness but from physics. Navigation and science share the same radio. Doppler tracking measures frequency shifts caused by relative motion, turning the carrier into a velocity probe, where tiny changes in hertz translate into meaningful changes in meters per second. The measurement relies on extremely stable frequency references on the ground, because drift can masquerade as motion. In this way, timekeeping becomes navigation, and navigation becomes another form of listening. Small Doppler changes reveal trajectory, gravitational influences, and subtle forces. Over long baselines, Doppler becomes a precision tool for knowing where Voyager is, even when the spacecraft is too far for any optical tracking to be practical. The craft's position is inferred from the behavior of a radio wave, not from a visible dot in a telescope. It is a reminder that exploration can be done with mathematics as much as with cameras. The DSN does more than listen. It provides timing, frequency standards, and calibration that keep the conversation coherent across decades, so that a signal transmitted by a 1970s oscillator can still be interpreted by modern ground systems. Ground upgrades become part of the mission's longevity, extending the life of the spacecraft by improving Earth's ears. In a sense, Voyager survives partly because Earth keeps changing. As the spacecraft ages, the ground system must age with it. Receivers are upgraded, signal processing improves, and the network learns new ways to hear old hardware, extracting meaning from signals that would once have been dismissed as noise. Better algorithms can pull weaker carriers from the background, and better scheduling can give longer listening time when needed. The spacecraft remains the same, yet the conversation becomes more sophisticated. This partnership is asymmetrical, but real. Voyager provides data, and Earth provides interpretation, commands, and the infrastructure that makes bits arrive, along with the institutional memory that keeps the mission legible across generations. The spacecraft is an artifact of the 1970s, but the mission is a living system in the present. The continuity is maintained by people who inherit a machine and learn its language. Power decline ties every theme together. Less power means fewer heaters, which means colder electronics, which means higher risk, which means more conservative operations, and conservatism itself can reduce science return by limiting what is attempted. The chain is not theoretical, it is operational, and it tightens year by year. In the outer dark, every subsystem becomes a lever on every other subsystem. Less power also means weaker transmitters or shorter contact windows. The mission becomes a constant negotiation between keeping the craft warm and keeping it heard, because a warm spacecraft that cannot downlink is still, in practice, silent. Engineers sometimes face choices that feel philosophical, because they weigh survival against expression. What is the value of staying alive if you cannot communicate what you learn? Engineers build power tables that forecast the future. They plan years ahead, deciding which instruments will be the last ones standing, and they revisit those plans as real performance diverges from models in small consequential ways. Forecasts include not just RTG decay, but temperature effects, load changes, and the gradual loss of efficiency and conversion. The future arrives as a set of numbers, then becomes a set of constraints. These forecasts are not merely technical documents. They are a narrative of remaining time, where each line item represents a capability, and each capability represents a kind of question that might be asked one last time. A heater line is not just a heater, it is the continued stability of an oscillator, and therefore the continued clarity of a radio link. A few watts saved can be a year gained, and a year gained can be a discovery. The drama is not a single failure, but a gradual narrowing of possibility. Voyager survives by becoming smaller in function while staying coherent in purpose, a long lesson in how endurance is often indistinguishable from adaptation. The craft does not triumph by resisting change, it triumphs by accommodating it. The mystery is that adaptation can be engineered, not just hoped for. This slow shedding heightens the mystery rather than ending it. Each shutdown makes the remaining measurements more precious, because there will be no replacement, and because the environment being measured is itself changing with distance. The farther out you go, the less you can compare your data to anything familiar. The mission becomes a single thread of evidence stretching into a region no spacecraft had ever sampled. The spacecraft is now an outpost at the edge of the sun's influence. It measures a fading wind, a changing magnetic field, and a rising background of galactic particles, where the local space begins to feel less solar and more cosmic. The numbers tell a story of pressure and balance, of a star pushing outward against an interstellar medium pushing back. The boundary is not a line on a map, it is a living interface. The cosmology tie-in is not poetic, it is literal. As Voyager moves outward, the sun's energy becomes a diminishing term in the equations, and the probe's instruments become a way to watch that diminishing happen in real time. The heliosphere is shaped by flows and fields, and those flows and fields are measurable only with persistent presence. Voyager's endurance turns a theoretical boundary into a monitored environment. Solar photons weaken with the inverse square of distance, and the solar wind thins as it expands. The heliosphere is built from that weakening, shaped by external pressure, and defined by a balance between what the sun pushes out and what the galaxy pushes back. That balance can shift with solar cycles, and it can ripple with shocks from solar eruptions. The boundary breathes, and the spacecraft is there to notice. Voyager's engineering constraints echo that same geometry. Power falls, warmth falls, and the ability to send information falls, mirroring the sun's fading reach, until the spacecraft itself becomes an analogy you can measure in watts and bits. The craft is a physical embodiment of the inverse square law, living inside it rather than merely describing it. In that sense, engineering becomes a kind of cosmological instrument. This is why the boundary matters to our place in the cosmos. The heliosphere is not just a map feature, but a shield and a definition of neighborhood, filtering particles and shaping the space weather that reaches the inner planets. It modulates radiation exposure, and it influences the energetic environment through which planets move. Understanding its edge is part of understanding what protects and what exposes worlds like ours. Voyager's continued operation turns the boundary into a measurable, contested thing. It replaces a cartoon edge with gradients, shocks, and transitions, and it forces scientists to ask what outside even means when the boundary is thick and dynamic. If the heliosphere has layers, then crossing it is not a moment, it is a process. What else in the cosmos is drawn as a line, when it is really a region? The mission's greatest trick is endurance without repair. It is a machine designed to fail gracefully, giving up parts while keeping the core alive, and doing so in a way that leaves the remaining data stream scientifically interpretable. Graceful failure is not resignation, it is strategy, because it preserves continuity. Continuity is what makes long baseline measurements meaningful, especially at the edge. That design philosophy is conservative, but it enables discovery. It keeps a thread of measurement unbroken long enough for the sun's domain to reveal its true scale, and it turns engineering discipline into a kind of observational patience. Patience is not passive here, it is active management of risk and resources. The spacecraft survives because it is constantly being simplified, carefully and deliberately. There is also a human timescale hidden inside this patience. Teams change, tools change, and even the language of computing changes, yet the spacecraft continues to answer in the same sparse telemetry words it has always used. The people listening are often younger than the mission itself, inheriting a machine older than their careers. In that continuity, Voyager becomes not just a probe, but a long-running relationship between hardware and human attention. Still, the story cannot stay in the dark forever. Survival is only meaningful because it carries Voyager to encounters that reshape expectations, where the careful budgeting of watts and degrees translates into minutes of priceless data. The engineering is the quiet prelude to spectacle, the scaffolding that makes discovery possible. Without endurance, there is no revelation, only a brief flash and then silence. With the craft's endurance secured, the outward road returns to spectacle and danger. Voyager meets the first major character in its planetary saga, Jupiter, where the solar system becomes stranger than predicted, and where every assumption about what a planet can be will be tested. In the visuals, the giant world swells from a bright point into a banded disk, and the mission's long preparation finally meets its first great trial. Jupiter is the first true test of Voyager's endurance inside a hostile planetary system, and it announces itself in radio long before it fills the camera frame. In the months before arrival, while Jupiter is still a bright star among stars, the spacecraft's receivers begin to notice a growing structured roar. It is not a single tone, but a shifting landscape of emissions, evidence that the space around the planet is already crowded, energized, and electrically alive. Long before closest approach, the instruments register a storm of charged particles, as if the vacuum itself has become a medium with weather. The magnetometer, built to sense tiny changes in field direction and strength, sees a magnetic environment far stronger than Earth's, and it senses that field rotating with a 10-hour day. Even at great distance, the signal carries the signature of a spinning source, like a lighthouse beam made of magnetism rather than light. That rapid rotation matters, because Jupiter is not merely large, it is fast, and it is electrically muscular. Beneath the cloud tops, pressures climb until hydrogen behaves like a conductor, and the planet's deep interior becomes a generator. The dynamo is driven by rotation and convection, and it produces an immense magnetic field, an invisible structure that extends millions of kilometers into space. Jupiter's magnetosphere is not a simple bubble pushed back by the solar wind, like a balloon in a steady breeze. It is a spinning engine that drags plasma, accelerates particles, and builds lethal radiation belts that can punish any unprotected electronics. The solar wind still matters, but here it is negotiating with a system that has its own momentum and its own internal supply of charged material. In the black between planets, Voyager is still whispering to Earth from the dark in our present. Here in 1979, it is learning how loud the solar system can be, and how violence can hide inside emptiness. The encounter is a reminder that space is not a perfect void, because fields and particles can turn it into a working machine. The first signature is sound, even though space itself is silent and offers no air to carry a wave. Voyager measures intense radio emissions tied to magnetic fields and particle interactions, and those measurements arrive as patterns, frequencies, and amplitudes, rather than anything a human ear could hear. The data looks like mathematics, but it carries the emotional weight of a warning, because the environment is speaking in its own language. Engineers translate those frequencies into audio for human ears, mapping radio bands into a range we can perceive. The result is an eerie rising and falling tone, like a scream shaped by physics, and it feels personal even when it is purely mechanical. In control rooms and laboratories, the sound becomes an uncanny bridge, numbers turned into something that can be felt in the body. That scream is not metaphorical in the data, and it is not a trick of interpretation. It is cyclotron and plasma wave activity, driven by electrons spiraling along magnetic field lines, emitting radio energy as their motion couples to the electromagnetic environment. The emissions are organized by geometry, because the field lines guide particles the way rails guide a train. The mechanism is precise, and it is familiar to plasma physicists. Charged particles gyrate around magnetic field lines at a frequency set by the field strength, and when conditions align, the system radiates powerfully, an audible ghost of electrodynamics. In plain terms, electrons are being forced into orderly motion, and that forced motion leaks energy as radio waves. Jupiter's auroras are part of the same circuit, and they are not simply pretty lights. Particles rain into the poles along magnetic funnels, they collide with atmospheric gases, and the radio emissions track the changing geometry of that invisible conduit. What Voyager hears is connected to what a camera might see, because both are expressions of the same currents. From a distance, Jupiter's poles are small caps on a massive sphere, but the auroral engine is vast. The auroras can brighten and shift as the magnetosphere breathes under solar wind pressure and as currents surge through the planet's upper atmosphere. The brightness is not steady decoration. It is a readout of energy being deposited moment by moment into gas. The system behaves like a miniature solar system, with its own weather of fields and particles. Moons orbit inside a magnetized environment that can dominate their surfaces, and the space between them is not empty so much as electrically structured. Invisible boundaries, current sheets, plasmatory, radiation zones, divide the darkness into regions with distinct hazards and distinct signatures. Radiation becomes the immediate operational threat, because Jupiter's belts are not theoretical lines on a diagram. They are regions of energetic electrons and ions that can damage electronics, fog camera sensors, and flip bits in memory with a single unlucky strike. A particle that is microscopic in mass can still be catastrophic in effect, because it carries energy measured in millions of electron volts. Voyager's survival is not guaranteed by design alone, even though it was built with deep space in mind. It depends on operational choices made in advance, when the spacecraft is still days away, and every decision must be made with incomplete information. Planning becomes a form of navigation, because the route is not only through space, but through risk. Teams plan exposure times and instrument duty cycles around predicted radiation peaks, using models built from earlier missions and ground-based observations. Those models are imperfect, because Jupiter's system is variable, and the solar wind can compress or relax the magnetosphere. They decide when to run cameras, when to pause, and when to accept risk, because the encounter is a one-time passage. Some imaging sequences are shortened to reduce time in the worst zones, and the trade is painful. Every lost minute might mean a missed frame, but every extra minute in the belts is cumulative damage that cannot be repaired across hundreds of millions of kilometers. The mission is always balancing two kinds of loss: lost data now or lost capability later. Some instruments are powered strategically, because turning something off is sometimes safer than letting it endure. The spacecraft's computers and memory are vulnerable to energetic particles, and even a brief upset can corrupt data or force a protective reset. In a system where seconds matter, a reset is not merely an inconvenience, it can be a missed world. The spacecraft's shielding is modest because mass was limited at launch and every kilogram mattered. Protection comes from distance, timing, and the discipline to keep the encounter brief, as if the mission is threading a needle through a storm. Engineers rely on redundancy and careful sequencing, but they also rely on luck because radiation is statistical and unforgiving. Jupiter's rapid rotation amplifies everything, and it does so relentlessly. A strong magnetic dipole, tilted and spinning, sweeps particles around like a generator with no off switch, converting rotational energy into electromagnetic motion. The field does not merely sit in space. It drags, shears, and accelerates what it captures. The magnetosphere captures ions and electrons from the solar wind, but it does not rely on the sun alone. It also captures material from inside the system, creating a local source of plasma that feeds the belts and thickens the environment. This is one of Jupiter's defining differences. Its magnetosphere is not only a shield, but a factory. That source is Io, a moon that should have been inert in the cold, at least by the old expectations. Instead, it feeds Jupiter's magnetic environment with sulfur and oxygen, and it does so continuously, as if it is bleeding atmosphere into space. The idea is counterintuitive, a small moon influencing a giant planet's space weather. Voyager's instruments detect a donut of plasma along Io's orbit, and the geometry is unmistakable. It is a torus of ionized material, trapped and forced to co-rotate with Jupiter, even though it originates from a moon that is orbiting independently. In data plots, the torus appears as a persistent enhancement, an electrical ring marking Io's path. The physics is direct and universal, but it is startling to see it at such scale. Neutral atoms escape Io, become ionized by sunlight or particle impacts, and are picked up by magnetic fields as new charged particles. Once ionized, they are no longer free to drift because the field line becomes a constraint that defines their motion. Once captured, they are accelerated by the rotating field, and the magnetosphere becomes a particle accelerator powered by angular momentum. The faster Jupiter spins, the harder it drags the plasma, and the more energy the particles can gain. In practical terms, the planet is spending a small fraction of its rotational energy to keep the belt stocked and dangerous. In this system, magnetism sculpts geography without touching rock, because it sculpts the environment that touches rock. Radiation patterns map the field lines, and those field lines map the planet's internal dynamo, revealing an interior we cannot see. The invisible becomes measurable, because charged particles act like ink tracing the lines of force. Voyager's magnetometer reads the dynamo's reach as the spacecraft moves through different regions of space. The field strength and orientation change with position. Outlining a structure larger than the Sun could illuminate in a single glance. The measurements are also time-stamped, because rotation means the environment changes even if the spacecraft held still. The danger and the discovery are linked, and that link is the story's tension. The same trapped particles that threaten cameras also reveal the system's architecture through their flux and energy, turning hazard into measurement. Voyager is, in effect, using the storm as a probe, letting the environment announce itself through its own violence. As Voyager closes in, Jupiter's moons stop being points of light and become worlds with distinct surfaces. Each one is shaped by a different energy budget, and each one carries clues about how the Jovian system works as a whole. The camera's resolution improves frame by frame, and the solar system's largest planet begins to feel like a neighborhood rather than a destination. Even before the best images arrive, there is a sense of scale that is difficult to hold in the mind. Jupiter's disk swells in the frame, its cloud bands sharpen into textures, and the great red spot becomes a storm with a history. The planet's curvature is obvious now, and the limb is edged with faint haze, an atmosphere deep enough to swallow Earth. The planet's atmosphere is a layered machine of ammonia clouds, deeper hazes, and darker belts where warmer material rises. The colours, creams, browns, and muted reds, trace chemistry and circulation, and they hint at heat still escaping from within. Jupiter radiates more energy than it receives from the Sun, and that internal heat helps drive its restless bands. Yet the chapter's focus is not Jupiter's clouds, but the moons that move through its electromagnetic reach. Their surfaces are the pages on which gravity and radiation have been writing for billions of years. Each moon is a different experiment, run under the same magnetic sky, with different materials and different outcomes. Io looks like it should be cratered like the moon, because impacts are the default sculptor in the solar system. Instead, it appears strangely young, with few impact scars and broad planes of unusual colour that look painted rather than pulverised. The absence is itself a presence, evidence that something has been erasing the past. The palette is unsettling, because it does not match familiar rock. Yellows, oranges and blacks spread across the surface in irregular patches, and the terrain looks as if it has been resurfaced, smoothed and stained by something active. The colours suggest sulfur compounds and volcanic deposits, but in 1979 those words still feel like speculation. The first interpretation is confusion, and it is an honest scientific moment. A surface without craters suggests resurfacing, but the mechanism is not obvious at Jupiter's distance from the Sun, where sunlight is weak and temperatures are low. The old mental model, small equals cold, cold equals dead, begins to fracture under the images. Then the frames show something no one expected to see in real time, not as a frozen relic but as an event. A plume rises above Io's limb, and the shape changes between frames, as if the moon is exhaling into space. Against the black background, the plume's curve is crisp and its scale is unmistakable. The plume is not a subtle haze, and it is not a trick of lighting. It arcs upward in a clean, bright shape against darkness, and it casts a sense of motion into still photographs, because the eruption is happening during the flyby. The geometry implies ballistic motion, material thrown upward, then falling back under Io's weak gravity. Voyager has found active volcanism on another world, and the discovery lands with a strange immediacy. It is not a fossil record of ancient heat, but a present tense eruption, witnessed across hundreds of millions of kilometres. For planetary science, it is a hinge moment, proof that geology is not confined to Earth. The discovery rewrites the definition of a moon, because moons were expected to be small, cold, and geologically dead. Io is not a dead satellite, but a geologically alive body with heat escaping through vents, fissures, and caldera-like depressions. The surface features begin to read like volcanic landforms, even when the materials are unfamiliar. In the frames that follow, the surface looks less like a cratered sphere and more like a landscape in flux. Broad flows appear to have buried older terrain, and the lack of small craters suggests that the burial happens again and again. Resurfacing is not a rare catastrophe here. It is a steady rhythm, paced by orbital mechanics. The question becomes the power source, and it becomes urgent because the evidence is so direct. Sunlight is weak at Jupiter, and radioactive decay alone seems insufficient for such intense activity on a body Io's size. If the heat is real, then something is paying the energy bill, and the accounting must close. The answer is gravity, applied repeatedly and with exquisite persistence. Io is flexed by Jupiter's tides, and the flexing turns orbital energy into internal heat, the way bending a metal wire warms it if you do it long enough. The comparison is simple, but the underlying process is rigorous mechanics acting on a planetary scale. Tidal heating is not a vague squeeze, and it is not a poetic metaphor. It is mechanical work done on rock, dissipated as friction as the moon deforms and relaxes, and the energy becomes heat inside the crust and mantle. In more technical terms, the changing tidal potential drives strain, and the strain is damped by the moon's imperfect elasticity. Io's orbit is not perfectly circular, and that detail is the key that keeps the furnace running. Eccentricity makes the tidal bulge shift around the moon, forcing continual kneading rather than a static distortion that would quickly settle. If the orbit was circular, the bulge would become steady, and the heating would diminish as the system relaxed. As Io moves closer and farther from Jupiter during its orbit, the tidal pull changes, and the moon flexes accordingly. The rock does not respond elastically forever. It dissipates energy, and that dissipation can melt material and drive eruptions. Over time, the interior becomes a heat engine, turning orbital motion into magma and gas. That eccentricity is maintained by resonance, and resonance is an architectural feature of the Jovian system. Io, Europa, and Ganymede are locked in a repeating orbital rhythm that prevents circularization, keeping the flexing alive over long time. Their periods form a stable pattern, and that pattern acts like a metronome for tidal stress. The resonance is a gravitational engine, and it runs with the steady patience of celestial mechanics. Each moon tugs the others at regular intervals, pumping energy into their orbits and into Io's interior, sustaining heat that would otherwise fade. The system is not chaotic in its timing, even if its consequences are violent. This is the deeper surprise inside the volcanic plumes. The moon is not choosing to be active. The system is forcing it, and the forcing is written into the timing of orbits that repeat with clock-like regularity. In a sense, Io is paying for the stability of the resonance with its own internal strain. Voyager's data does not just show volcanoes, and it does not merely add a new feature to a catalogue. It shows a system where orbital mechanics becomes geology, and where time-dependent gravity makes heat in the cold. The discovery also forces a re-evaluation of earlier assumptions, because it implies that other moons could be active in quieter ways. The implications are immediate for Jupiter's environment, because Io's volcanism is not isolated from space. Eruptions loft sulfur-bearing gases and dust, some of which escapes, becomes ionized, and feeds the plasma torus that Voyager measures. The moon is not only a world, it is a source region, a supplier feeding the magnetosphere's appetite. So the story loops back on itself, and the loop is elegant. Io's internal heating drives volcanism, volcanism supplies material to space, and that material becomes plasma that strengthens the radiation environment that threatens the spacecraft. The same eruption that astonishes the cameras also helps build the belts that endanger them. In this system, a moon can shape a planet's magnetosphere, and a magnetosphere can shape a moon's surface. Cause and effect trade places, and Voyager is trying to measure both at once while racing through a dangerous corridor. It is a rare moment when planetary science feels like ecology, interactions, feedbacks, and consequences across scales. Europa enters the story as a contrast that feels almost deliberate, as if nature is offering a controlled experiment. Where Io is fire, Europa is ice, bright and smooth under a dim sun, reflecting light like a polished stone. The brightness is striking in the images, and it makes Europa look clean, almost luminous against Jupiter's darker backdrop. At first glance, Europa seems quiet, and its brightness reads as cleanliness. Then the images resolve a surface crisscrossed by long dark lines, cutting across planes with little topography, like cracks in glass that never shattered completely. The lines are not random scratches, they're global scale features, and they demand interpretation. These linneae suggest a crust that has cracked and shifted, and the geometry is hard to dismiss. The patterns look like fractures that opened, moved, and were filled or refrozen, leaving dark seams that trace stress across a global shell. The dark material could be briny residue, radiation-altered ice, or debris mixed upward from below. Some lines run for hundreds to thousands of kilometers, and they curve as if responding to a changing stress field. They cross one another in layered histories, implying that the surface has been strained repeatedly rather than broken once. The crossings read like timelines, older fractures cut by younger ones, a record written in intersecting scars. In places, the surface appears broken into plates and jumbled blocks, as if the ice has been disrupted and rearranged. Chaotic terrain hints at disruption from below, not just impacts from above, and it suggests a crust that can move. The texture looks like a frozen sea that has been shattered and refrozen, leaving rafts locked in place. Europa's relative lack of craters repeats Io's clue in a different language, and it demands the same question. The surface appears young, implying resurfacing over geologic time, because impacts should accumulate if nothing erases them. When a world is smooth, the smoothness is evidence, and the evidence points to process. The resurfacing mechanism points downward, and it is easier to imagine once the material is ice. Ice can flow, ice can fracture, and ice can be renewed if there is heat beneath it, even if the surface remains bitterly cold. The shell could behave like rock in slow motion, deforming over time while still appearing rigid in a single photograph. Voyager's spectroscopy adds chemical hints, and those hints are subtle but important. The reflected light is consistent with water ice, altered by radiation, and mixed with darker materials that may be salts or sulfur compounds delivered and processed over time. Spectral fingerprints are not pictures, but they are constraints, narrowing the range of plausible surface compositions. Charged particles from Jupiter bombard Europa's surface, and the bombardment is constant. Radiation chemistry can modify ice, breaking molecules and creating new compounds, and those changes alter the spectral signature that instruments can detect. The surface is being processed from above, and that processing can mask or reveal what lies beneath. The same magnetosphere that threatens Voyager also processes Europa, and it does so grain by grain. It drives sputtering, implantation, and a slow erosion that can feed a tenuous atmosphere, built from molecules knocked free by energetic impacts. Europa's environment is therefore a blend of geology and space weather, surface and magnetosphere in continuous exchange. Europa's cracks suggest mobility, and mobility suggests a mechanical explanation rather than a purely cosmetic one. If the crust is floating, then a liquid layer beneath becomes plausible, acting as a lubricant for shifting ice and refreezing fractures. The idea is simple to say, but profound to accept. Liquid water could persist where sunlight is weak. The case for an ocean is not proven by one image, and it is not a single dramatic plume like Io's. It is built from multiple lines of evidence that converge on a warm interior, where heat and stress can keep water from freezing solid. The argument is cumulative. Youthful surface, fracture patterns, chaotic terrains, and chemistry that hints at something more than pristine ice. Tidal heating provides the candidate energy source again, but its expression can be gentler here. Europa is also flexed by Jupiter, and resonance keeps that flexing from fading away, delivering energy into ice and perhaps into a hidden sea. The heating may be distributed differently because ice responds differently than rock, and because Europa's interior structure is not Io's. If Io's tides make volcanoes, Europa's tides could make melt, and the contrast is instructive. The same gravitational mechanism can produce radically different surfaces depending on composition, internal structure, and how efficiently a world sheds heat. One world vents heat in fire and sulfur, while another may store it beneath a shell that hides its motion. Europa's brightness, its smooth plains, and its dark seams become a quiet argument. They suggest that the surface is not simply ancient ice, but a shell that has been renewed, cracked, and possibly recycled by processes that require warmth below. The Moon's calm appearance becomes deceptive because the evidence points to activity that is slow, sealed, and persistent. The thought is unsettling in the best scientific way because it expands what active can mean. Activity does not always look like fire. Sometimes it looks like a fracture that opened, shifted, and sealed again over a dark ocean. The question becomes unavoidable. What else might be happening beneath surfaces that look still? Voyager's Jupiter encounter becomes a lesson in energy sources, and the lesson is larger than a single mission. Sunlight is not the only driver of activity, and distance is not the same as dormancy, even in the outer reaches of a system. The outer planets are not merely colder versions of the inner ones. They are different regimes, where different engines dominate. This is where planetary science touches cosmology, because the processes are local, but the principle is general. The same equations that describe rotating conductors and tidal dissipation apply wherever planets and moons form, including around other stars. Voyager's measurements are therefore not only about Jupiter, but about the universality of physics. Magnetic fields arise from rotating conducting interiors, not from special circumstances reserved for giants. Plasma interactions follow the same electrodynamics everywhere, given particles and fields, and the resulting emissions can be read like signatures across space. A radio scream is, in that sense, a diagnostic, a clue that a magnetized engine is operating. Tidal heating depends on gravity and orbital architecture, and architecture is a common outcome of formation. Those ingredients are common in multi-moon systems and in exoplanet systems with resonant chains, where repeated tugs maintain eccentric orbits. The Jovian resonance becomes a template, suggesting that other systems may hide their heat in the same way. A world can be warm in the dark if it is mechanically worked by tides, and that statement changes the map. Habitability becomes a question of energy flow, not just distance from a star, because heat can come from motion as well as light. The idea does not guarantee life, but it widens the list of places where chemistry could stay active. The classical habitable zone is a useful first filter, and it remains a powerful idea. Voyager's moons suggest that subsurface environments may persist far beyond it, protected from vacuum and radiation by kilometers of ice that act as insulation. If an ocean exists, it would be dark, pressurized, and isolated, yet potentially stable over immense spans of time. Jupiter's system therefore expands the map of possible living niches, even if it offers no direct evidence of life. It shows that chemistry and liquid water might exist under ice, protected from radiation above and sustained by tides below. The concept is both hopeful and humbling, because it implies that the most interesting habitats may be hidden from view. The central question returns in a new form, and it becomes harder to ignore. If the Sun's domain has an edge, then life's domain may have unexpected extensions within it, hidden not in warmth, but in protected pockets of energy. The question lingers like the fading radio tone. What counts as a habitable world when the heat source is gravity? Voyager's measurements at Jupiter also foreshadow the later Interstellar story, because boundaries repeat across scales. Magnetospheres and shock fronts are not unique to planets, but appear at larger scales, wherever flows of plasma meet resistance. The spacecraft is learning to recognize transitions that have no visual marker, only changes in particles and fields. Jupiter's magnetopause is a local boundary with the solar wind, and it shifts as pressure changes. The heliopause will be the Sun's boundary with interstellar space, shaped by similar pressures, and Voyager is learning the language of those borders. The same logic applies: measure the field, measure the particles, and infer the shape of an invisible frontier. In both cases, fields and particles define the frontier more than visible matter, and the frontier is dynamic. Voyager learns to read those frontiers through flux changes and field rotations, noticing when the environment transforms without any visible sign. The lesson is subtle but essential. In space, the most important structures are often the ones you cannot photograph. The encounter ends quickly, because flybys are brief by design, and because danger imposes its own schedule. The spacecraft leaves Jupiter with a new trajectory and a new understanding of risk, carrying data that will take months to fully interpret. The images arrive as strips and mosaics, the measurements as tables and plots, and the meaning emerges slowly as teams compare instruments and reconcile anomalies. The scream fades with distance, But the lesson remains, and it remains in the numbers. The outer solar system is not quiet, and emptiness can still be violent, because fields and particles can turn space into a working machine. Jupiter has shown that environment is not only atmosphere and surface, it is also radiation, plasma, and invisible motion. Jupiter has given Voyager a system that behaves like a laboratory, but it is a laboratory with consequences. It is a place where gravity, magnetism, and chemistry interact at planetary scale, and where a moon's interior can influence a planet's space weather. The results are not abstract because they determine what a spacecraft can survive and what it can see. It has also given the mission a new narrative tension that will not disappear. Survival is not just about power and time, but about passing through environments that can erase instruments, scramble data, and end a story mid-sentence. Every future encounter will carry Jupiter's warning. Beauty does not imply safety, and distance does not imply calm. Yet the payoff is unmistakable, and it is written in images that still feel fresh decades later. 2 small moons have rewritten the rules, proving that active worlds can exist far from the Sun and that the definition of dead must be earned. The discoveries are not footnotes, they are foundations for how we now think about moons, oceans, and planetary systems. From Jupiter's chaos, the mission turns toward the next gate in the Grand Tour, and the path is set by gravity. Saturn waits ahead with a different kind of order and different hidden hazards, and Voyager carries Jupiter's lessons like a warning. The spacecraft is still the same machine, but the story around it has changed, because now we know what the outer solar system can do. The transition is not relief, but contrast, and contrast can be deceptive. After the screaming planet, Voyager approaches a world of rings, haze, and quieter elegance, where beauty can hide complexity and danger in plain sight. The radio environment softens, the immediate radiation threat eases, and the visuals begin to promise symmetry, yet the unknown is still ahead. And the central question keeps travelling with it, because it is larger than any single planet. Each system crossed is a clue about how boundaries form, and how far a star's influence can truly reach, through light, through gravity, and through fields. Voyager is not only moving outward, it is moving into a broader definition of what a planetary system is. With the craft's endurance secured, the outward road returns to spectacle and danger, and the next chapter waits in Saturn's shadowed glow. Saturn arrives as a different kind of shock, not loud like Jupiter, but intricate and almost mathematical. Voyager has crossed from brute force into structure, where gravity writes in fine lines and small forces accumulate into architecture. The planet's presence feels calmer at first glance, yet the calm is deceptive, because the details multiply the closer you look. From far away, Saturn seems simple, a pale globe with a bright halo that looks painted on. The disk is buttery and subdued, its cloud bands softer than Jupiter's, as if the atmosphere is holding its breath. As Voyager closes in, the halo breaks into countless parts, and the system stops behaving like a picture and starts behaving like a machine. The camera's first close frames do something unsettling to the eye, because they violate scale. What looked like a single ring becomes layered brightness, then braided bands, then thin threads that seem too sharp to be natural. The contrast is so clean that it resembles engraving, light and dark lines etched into space. The rings are not a solid sheet, and they are not a static ornament hung in space. They are a disk of icy particles, from dust grains to boulders, each obeying gravity while acting together like a fluid. The word icy is not decorative here, because water ice dominates the reflectivity and controls how sunlight scatters back toward the camera. That fluid comparison is not a metaphor meant for poetry, it is a physical clue. When countless particles collide and exchange momentum, the group can spread, damp, and flow in ways that resemble viscosity. Each collision is tiny, almost trivial, yet the collective outcome becomes measurable, like a slow, cold weather system made of orbiting ice. Voyager's first task is to turn beauty into a physics problem, and it does so with discipline. The camera and photopolarimeter do not just record brightness. They map angles, polarization, and scattering that must be explained. This is how a ring becomes a laboratory sample, even though it is hundreds of thousands of kilometers wide. Brightness is not simply more ice or less ice, because light interacts with texture. A ring made of clean frost reflects differently than a ring dusted with darker contaminants, and polarization can reveal grain size and roughness. Even the way shadows fall across the ring plane matters, because shadow length encodes particle height and the thickness of the disk. Up close, the rings resolve into ringlets, gaps, and sharp edges that should not persist for long. The old idea of a few broad rings collapses into hundreds of narrow structures, some only tens of kilometers wide. In orbital terms, that is razor-thin precision, maintained inside a system that should naturally smear and blur. The visuals become almost architectural, like looking down on a city at night. Bright lanes run parallel, dark channels cut between them, and every boundary seems drawn with a ruler. The planet hangs beyond like a dim lamp while the rings gleam as if they are lit from within. Some gaps are clean and deep, like missing lanes in a crowded highway that never fills back in. Others are partial, filled with faint material that hints at ongoing transport and constant rearrangement. The emptiness is rarely absolute, which is a clue that ring matter is always migrating. Slowly, reluctantly, but continuously. Even the names scientists use carry the history of earlier telescopes and earlier guesses. The Cassini division, once thought nearly empty, becomes a region with its own ringlets, as if division was always an oversimplification. The name reaches back to Giovanni Domenico Cassini in the 17th century, when Earth-based optics could only hint at the ring's true complexity. That historical arc matters because Saturn's rings have always been a test of perception. Galileo saw ears on Saturn and could not interpret them because his telescope was too crude to resolve a ring. Later observers argued over whether the rings were solid, liquid, or made of countless small bodies, and Voyager arrives as the first witness with the power to settle many of those debates. Voyager finds spokes, transient dark features that appear and fade across the B-ring with eerie speed. They look like radial shadows laid over circular motion, and they refuse to behave like simple orbital streaks. In a system built from near-circular orbits, radial marks feel like a contradiction, which is why they seize attention. On film, a spoke can form, stretch, and dissolve within hours, which is fast on a planetary scale. That speed implies a process that is not just slow gravitational sorting, but something that can switch on and off. The rings begin to feel less like geology and more like weather. Events that happen, not just structures that exist. The spokes force a new category of explanation, where dust, charging, and Saturn's magnetosphere matter. A ring becomes an electrical environment, not only a gravitational one, and that shift changes the vocabulary. The planet's magnetic field is invisible in the images, yet it becomes present through its effects, like wind inferred from moving grass. Tiny grains can pick up electric charge from sunlight, plasma, and energetic particles trapped by Saturn's magnetic field. Once charged, they can be nudged by electromagnetic forces, lifting slightly above the ring plane and changing how they scatter light. That small vertical lift is enough to alter brightness and cast subtle shadows, turning electrodynamics into visible pattern. A spoke, in that view, is not a solid object moving like a moon. It is a pattern, an organized disturbance, made visible because charged dust briefly behaves differently than the heavier ice blocks around it. The heavier particles keep obeying gravity almost alone, while the smallest grains briefly join a second set of rules. The rings also show waves, ripples that travel through the particle disk like sound through air. Voyager's images reveal spiral density waves and bending waves, each with a precise wavelength that can be measured frame by frame. The spiral geometry is not artistic flourish, because differential rotation naturally winds disturbances into spirals over time. A density wave is a traffic jam in orbit, where particles bunch and thin in a repeating pattern. A bending wave is different, a vertical corrugation that tilts the ring plane, as if the disk is being gently plucked. Both can coexist in the same region, which tells scientists that multiple forcing mechanisms are operating at once. Those wave patterns are not decoration, they are encoded measurements hidden in plain sight. Their spacing and amplitude carry information about surface density and the ring's mass distribution, which cannot be weighed directly. The ring becomes a kind of instrument panel, where gravity writes its diagnostics into the arrangement of ice. In practice, scientists treat the ring like a detector, because it responds predictably to forcing. If you know what is pulling, and you measure the wave's shape, you can infer how much material is resisting. That resistance depends on how crowded the ring is, how often particles collide, and how strongly their self-gravity tries to keep them together. Resonances with moons provide the clockwork that drives many of these waves, and the clockwork is precise. When a moon's orbital period forms a simple ratio with ring particle motion, repeated tugs add coherently. One pull is negligible, but a pull timed perfectly becomes cumulative, like a child pumping a swing with small repeated kicks. A resonance is a small force applied at the right time, over and over, until it becomes structure. The result is a wave that can be traced back to a moon's orbit, like a fingerprint traced back to a hand. Voyager's images let those fingerprints be matched, turning abstract orbital ratios into visible, measurable spirals. This is the same logic that can pump an ocean tide on Earth, except the ocean is a disk of ice. The ring responds because the timing is right, and the timing stays right for thousands of orbits. The persistence is what makes resonances powerful, because the system does not forget yesterday's tug. Voyager's data links specific ring features to specific moons, turning the system into a solved puzzle piece by piece. Gaps and edges become signatures of gravitational choreography, and the choreography has a cast list. Even small moons matter, because in a resonance a small mass can leave a large mark if it repeats its influence long enough. Some moons act as shepherds, confining narrow rings by pushing material inward and outward. The ring's sharpness becomes evidence of ongoing control, not ancient accident, because without confinement edges should blur. The shepherding concept is almost counterintuitive, because it says a ring can be maintained by constant disturbance rather than by stillness. The idea of shepherding changes how we imagine stability. A narrow ring is not a relic that somehow survived, it is a structure maintained by constant negotiation between orbiting bodies. Stability becomes dynamic equilibrium, order preserved by continuous balanced forcing. In this view, the rings are a laboratory for collective behaviour, and the laboratory is enormous. Countless collisions, tiny and frequent, create viscosity-like effects that spread and smooth material over time. The same mathematics used for granular flows on Earth can be adapted here, although the sand is ice and the floor is orbital motion. Particles collide, exchange momentum, and settle into a thin disk because energy is dissipated. Order emerges because random motion is damped, leaving near-circular orbits that share a common plane. If collisions did not happen, the ring would puff up and thicken, because nothing would remove vertical and eccentric motion. That plane is not guaranteed at birth, because impacts and captures can create chaos. The disk forms because collisions erase vertical motion, and because Saturn's gravity punishes inclinations by pulling everything toward the equator. The planet's oblateness also plays a role, subtly shaping orbital precession and encouraging alignment over long times. Shear is constant because inner particles orbit faster than outer ones, and the difference is relentless. That differential motion stretches clumps into streams, and it turns local disturbances into long spirals that wrap around the planet. The rings are therefore always mixing, even when they look calm in a single still frame. If you could hover above the rings, you would see a slow conveyor of motion. The inner edge would always be trying to lap the outer edge, and every small pile-up would be smeared into a curve. The pattern would feel hypnotic, because the motion is smooth, yet the consequences are sharp. Self-gravity matters even when each particle is small, because the ring is crowded. Groups of particles can briefly clump, then be torn apart by shear, leaving wakes that repeat like a texture. This is gravity operating at close range, where even weak attraction can matter when neighbours are always near. Voyager's ring images hint at self-gravity wakes, subtle brightness variations aligned with orbital motion. The ring is not uniform, it's a constantly forming and dissolving microstructure, like ripples in windblown snow. The analogy is useful because it captures the scale difference, tiny features repeating across a vast surface. The phrase wakes is literal in a dynamical sense, because the ring has flow. A particle's gravity can gather neighbours for a moment, and the gathered group leaves a trailing pattern before it is shredded. In the aggregate, those wakes influence how the ring transports angular momentum, which in turn controls how fast it spreads. This is where the documentary shifts from spectacle to mechanism, and the mechanism is surprisingly intimate. Saturn's rings show how simple laws produce complex patterns when repeated billions of times. The viewer is watching emergent behaviour, order arising from countless small interactions without any central designer. The rings also raise an uncomfortable question about time, because physics does not pause for beauty. If collisions and spreading are relentless, then sharp ring features imply youth, replenishment, or confinement. Every crisp edge is a kind of timestamp, asking whether the system is young or continuously maintained. A ring left alone should gradually diffuse, its edges softened by the same collisions that keep it thin. So when Voyager sees razor boundaries, it is seeing either a young system or an actively maintained one. The debate is not academic, because it connects to how often Saturn's system has been disrupted by impacts or moon breakups. Voyager cannot settle the age debate, but it makes the debate unavoidable and urgent. The ring system looks too structured to be merely leftover debris, yet too dynamic to be eternal. The tension becomes part of Saturn's personality, elegance paired with instability. Saturn's elegance becomes a tension engine, because every clean edge suggests an active process. The rings are not a fossil, they are a living disk shaped by ongoing forces that never stop working. Even the faint dusty rings, harder to see, suggest continual sources, because small grains should be swept away or darkened over time. That ring physics echoes the broader story of planetary systems, and the echo is not subtle. Disks, resonances, and migration are not Saturn-specific quirks. They are common outcomes of star and planet formation. The rings become a nearby demonstration of how disks respond to embedded bodies, which is a central theme in modern astrophysics. A protoplanetary disk is also particles acting like a fluid, also governed by collisions and gravity. Saturn's rings become a nearby analogue for distant systems we cannot resolve, a scaled-down model with visible equations. When we speak of viscosity in a disk around a young star, Saturn provides a tangible example of what that word can mean. When astronomers see dark gaps in young stellar disks, they suspect forming planets carving paths. Here, Voyager sees gaps and waves carved by moons, and the analogy becomes a bridge between solar system science and astrophysics. The bridge is powerful because it makes distant observations feel less abstract, as if the universe is repeating a familiar experiment at larger scale. Voyager's measurements therefore connect a local detail to cosmology, because the same math travels. The gravitational choreography that sculpts ringlets can sculpt gaps in young stellar disks, and can even shape how moons and planets migrate. Migration sounds dramatic, but it can be slow, an object trading angular momentum with a disk until its orbit shifts measurably. Yet Saturn is not only rings, and Voyager is not only watching a disk as it rushes past. The mission is also approaching moons that will force another shift in how we define a world. The ring plane becomes a foreground curtain, and beyond it the satellites wait like separate acts in the same play. The first moon that changes the story is Titan, because it refuses to be seen. Voyager aims its cameras, and the result is an orange sphere with no surface, like a planet wrapped in parchment. The colour is not just aesthetic because it signals complex organic haze suspended high in the atmosphere. In the approach images, Titan's limb is soft and glowing, and the light fades gradually into space. That gentle edge is the signature of a thick atmosphere, scattering sunlight high above whatever lies below. The glow makes Titan look larger than it is, because the atmosphere extends the visible boundary outward. Titan's haze is thick enough to hide continents, craters, and oceans if they exist. The frustration is immediate, because the most Earth-like moon is visually inaccessible at the very moment it becomes most interesting. The camera can only see the atmosphere's upper layers, and the surface remains a withheld secret. This frustration has historical weight, because Titan had been mysterious since its discovery in the 17th century. Christian Huygens identified it in 1655, and for centuries it remained a moving point of light with a stubbornly unreadable face. By the 20th century, ground-based spectroscopy hinted at methane, but the thickness and composition of the atmosphere were still contested. Voyager does not give up. It switches from seeing to inferring, and inference becomes the new drama. The infrared and ultraviolet instruments probe the atmosphere by absorption and scattering, reading chemistry from spectra. Where the camera fails, physics becomes a second set of eyes. A spectrum is a coded message because molecules absorb specific wavelengths like barcodes. When Voyager sees dips and peaks, it is not guessing, it is matching patterns to known molecular fingerprints measured in laboratories on Earth. The method is rigorous, yet it still feels like translation, turning faint lines into statements about air on a distant moon. The dominant signature is nitrogen, a surprise in abundance and in implication. Titan is not a thin exosphere. It is a deep atmosphere with pressure comparable to Earth's, pressing down on the unseen ground. That pressure implies a substantial inventory of gas, which raises questions about origin, retention, and long-term chemical cycling. Nitrogen also changes the story's tone because it is chemically familiar. It suggests an atmosphere that can buffer temperature and support complex reactions, even if the environment is far colder than any place humans could endure. In plain terms, Titan has air in a meaningful way, and that makes it feel less like a rock and more like a world. Methane appears as a key minor constituent, and it matters because it can drive chemistry. Under sunlight and particle bombardment, methane breaks and recombines into heavier hydrocarbons, building complexity from simplicity. Methane is also fragile on geological timescales, because sunlight should destroy it, which implies replenishment or hidden reservoirs. The sunlight at Saturn is weak, but ultraviolet photons still arrive, and Saturn's magnetosphere supplies energetic particles. Together they act like a slow, persistent spark, breaking bonds and letting new molecules assemble. The pace is gradual, yet over millions of years the chemistry can transform an atmosphere layer by layer. Those products build the orange haze, a photochemical smog that blankets the moon for hundreds of kilometers. Titan becomes a chemistry experiment, where simple molecules build complex organics over time, grain by grain. Some of those particles can coagulate into larger aerosols, then drift downward like soot in slow motion. In the visuals, the haze is not uniform, and that matters for interpretation. Subtle banding and brightness, gradients suggest layers, and layers suggest circulation, seasons, and a climate system that moves material around. Even without seeing clouds in the familiar Earth sense, the atmosphere hints at dynamics, air rising, sinking, and transporting haze across latitudes. Voyager's radio signal also becomes a probe during occultation, passing through Titan's atmosphere as the spacecraft slips behind the moon. Changes in the signal reveal density and temperature profiles, constraining pressure and scale height. It is a clever technique because it uses the spacecraft's communication link as a scientific instrument without adding any new hardware. Radio waves bend and slow when they pass through air, and the amount of bending depends on refractive index. By measuring that bending precisely, scientists reconstruct how density changes with altitude, like reading a vertical scan of an invisible ocean. The result is not an image, but it is still a portrait, one drawn in numbers rather than pixels. From those profiles, scientists infer a cold, dense lower atmosphere and a layered structure above. Titan's air is not uniform, it is stratified and dynamic, with temperature gradients that hint at weather. The data suggest that the atmosphere can support winds and perhaps precipitation, even if the precipitation is not water. The haze blocks the surface, but it also protects it, and protection is its own kind of revelation. Titan's lower atmosphere becomes a shield against radiation, creating a stable environment where chemistry can accumulate rather than be shredded. In a harsh outer system, that shielding is a form of habitability, limited, alien, yet scientifically provocative. That stability invites a question that hangs in the silence between images. If complex organics can form and persist, what other steps might chemistry take when given millions of years and a sheltered surface? And if Titan resembles an early stage of Earth's chemical history, what does it tell us about how common such stages might be elsewhere? The mission's limitation becomes the narrative point, and it lands with force. Voyager reveals that Titan is important, then it withholds the answer of what lies beneath, turning certainty into suspense. The orange glow becomes a promise that cannot yet be cached, and the audience is left with a deliberate ache of curiosity. That withholding is not failure, it is a new kind of discovery because it defines the frontier. A hidden surface means a hidden geology, and hidden geology means the story must continue beyond Voyager with new wavelengths and new strategies. The implication is clear. Radar, longer infrared observations, and future orbiters will be needed to peel the veil back. Titan also changes the definition of habitability in the outer system, even if no one expects forests or oceans of water. It is cold, yet it has a thick atmosphere, active chemistry, and energy sources beyond simple sunlight. In other words, it is a place where processes happen, and where time can build complexity rather than merely preserve ruins. The audience's mental model shifts again, from dead rocks to active systems that can run on different fuels. A moon can have weather, climate cycles, and chemical pathways that resemble prebiotic Earth, even under a dim sun. The resemblance is not perfect, but it is close enough to provoke a deeper question about what life-friendly truly means. Saturn's other moons deepen that shift, because some look impossible under older assumptions. They are small, bright, and strangely young, as if time has not touched them in the way it touches airless worlds. Voyager's images make the satellites feel like a gallery of exceptions, each one challenging a tidy rule. In the flyby imagery, crater counts become a kind of clock, because impacts accumulate steadily. When a surface has fewer craters than expected, it suggests that something has erased the record, and erasing requires activity. The logic is simple and powerful. If the scars are missing, something must have healed the skin. Enceladus stands out by brightness, reflecting sunlight like fresh snow under a black sky. High albedo is a clue, because space should darken surfaces through radiation chemistry and micrometeoroid gardening. The moon's glow looks almost artificial, a small lantern set against Saturn's enormous shadow. Those processes are slow but relentless, like sandpaper made of atoms and dust. Over time they redden and darken ice. So a bright world implies either youth or renewal, and both are provocative. The brightness also suggests that the surface is dominated by relatively clean water ice, not heavily mixed with dark rock or carbon-rich debris. A bright surface suggests resurfacing, and resurfacing suggests internal activity that brings fresh material up. Voyager's images show terrains that look smoother than expected, with fewer craters in some regions, as if the ground has been repaved. The repaving is not uniform, which implies localized processes rather than a single global reset. The smoothness is not featureless, and that is part of the mystery. Subtle ridges, fractures, and boundaries appear, hinting at tectonic stresses in ice, and hinting at a crust that can move rather than simply break. Ice at these temperatures can behave both as brittle rock and as slow-flowing material, depending on stress and timescale. The evidence is incomplete because the flyby geometry and resolution limit what can be proven. Still, the hints are strong enough to be unsettling, because they contradict the expectation of small moons as frozen fossils. The camera sees just enough to make the old story collapse, and not enough to replace it with a finished explanation. If Enceladus is being renewed, then something is supplying heat, and heat is hard to hide. Radioactive decay seems too weak for such a small body, so tides become the suspect again, with their invisible but persistent work. The idea is familiar by now, yet Saturn's system makes it feel newly general. An engine that can operate almost anywhere there is resonance. Saturn's moons interact gravitationally, and their resonances can pump eccentricities that would otherwise fade. Even small orbital deviations can generate flexing, and flexing can generate heat, like bending a paperclip until it warms. The heating is mechanical at heart, an orbital energy tax paid into the interior as friction. The heating is not evenly distributed, which makes it more interesting. It can concentrate along fractures, at poles, or in weak zones, creating localized geology that looks young even when the body is ancient. A small moon can therefore display a patchwork of ages, old cratered districts beside smooth provinces that appear newly made. Voyager does not yet see plumes, and it does not yet measure a subsurface ocean, because those tools and trajectories belong to later decades. It sees the first clues that later missions will reinterpret as cryovolcanism, and the reinterpretation is the point. The documentary's mystery deepens here, because the audience is watching the seed of a future revelation being planted. This is the chapter's central tension, built from what Voyager can and cannot do at Saturn's distance. The mission reveals complexity, then leaves gaps that become invitations for the future, and the invitations feel deliberate. The viewer is left with a sense that the solar system is not withholding information out of malice, but out of scale. Other moons add to the pattern of surprise, and the variety is itself a lesson. Some show fractured ice, some show smooth plains, and some show mixed terrains that imply episodic renewal rather than steady erosion. The differences suggest that each moon has its own internal budget, composition, heat, and stress, spent in different ways. In the visuals, the moons look like different experiments run under the same gravitational field. One is cratered like an old bone, another is bright and scarred, and another is wrapped in haze that refuses to reveal its face. Saturn's family begins to resemble a system of interacting environments rather than a set of passive ornaments. The system begins to look less like a museum and more like an ecosystem, where each body occupies a niche. Each moon is shaped by a different balance of tides, composition, and external bombardment, and that balance can shift over time. A slight change in resonance, or a change in orbital eccentricity, can alter heat flow and rewrite a surface's history. Tidal energy becomes the unifying engine across the outer solar system, and Saturn provides a clear demonstration. It converts orbital architecture into internal heat, and internal heat into geology and chemistry, even where sunlight is weak. The concept is profound in plain language. Motion can become warmth, and warmth can become change. This is not special pleading for one moon, it is a general mechanism with broad consequences. Wherever resonances persist, they can keep worlds warm in the dark for billions of years, and they can keep surfaces young. The implication stretches outward, because if tides can sustain activity here, then similar architectures around other planets may do the same. Saturn's rings and moons therefore become a single story about interaction rather than isolated objects. Moons sculpt rings through resonances, and rings record moon influences through waves and gaps, like a ledger written in ice. The ledger is constantly updated because the forces never stop and the particles never rest. The rings act like seismographs for gravity, responding to periodic forcing with measurable patterns. Voyager reads those patterns and turns them into mass estimates and constraints, translating brightness into numbers. In a sense, the spacecraft is listening to the system's rhythms, then converting those rhythms into physical properties. Even the spokes hint at coupling between ring particles and Saturn's magnetic environment. The system is not purely mechanical, it is electrodynamic and time variable, with behaviors that depend on plasma and sunlight. A ring can therefore change with local time, with season, and with the invisible weather of charged particles. That complexity matters to the documentary's larger arc, because it refines Voyager's education. Voyager is learning that boundaries and interfaces are where the action is, whether in rings or at the heliosphere's edge. Saturn provides a mid-course lesson in how invisible forces announce themselves through visible structure. A ring edge is a boundary maintained by resonances and collisions, always trying to blur and always being sharpened again. A moon's atmosphere is a boundary maintained by chemistry and escape, balanced against sunlight and particles. Each boundary is a negotiation, and the negotiation is where the science becomes most revealing. These are smaller versions of the same theme, an influence meeting resistance, and Saturn teaches the language. The heliopause will be the largest boundary Voyager crosses, but Saturn provides the grammar of interaction. It shows that the universe often speaks through edges, gradients, and transitions rather than through uniform fields. Saturn also forces operational humility, because rings are hazards as well as targets, and navigation is unforgiving. Trajectories must be precise, and encounter timing must respect a system filled with debris moving at orbital speeds. The beauty is therefore paired with risk, and the risk is not abstract when you remember the spacecraft is fragile. A particle the size of a pebble can be catastrophic at tens of kilometers per second, which makes the risk real. Voyager's path is planned to minimize exposure, and the planning becomes part of the story's quiet suspense. The spacecraft does not dodge in real time, because the distances make remote control impossible, so the caution must be built in beforehand. Voyager's survival depends on the same discipline described earlier, a countdown in watts, and a refusal to waste risk. Every instrument sequence is planned against power and time, and every observation is scheduled like a careful breath. At Saturn's distance, even transmitting data is an act of patience, because the signal is faint and the round-trip light time is long. The spacecraft is still whispering to Earth, and the whisper carries the first close evidence of a ring system behaving like a fluid. The data will outlast the images, because it can be reanalyzed as theories improve. What seems like a finished picture in one decade can become a new question in the next, when models grow more sophisticated. Titan's hidden surface becomes a promise that the solar system still has concealed chapters, even in places we thought we understood. Voyager has shown the question is real, and that the answer requires new tools, new wavelengths, and patience. The orange haze is therefore not just an obstacle, it is a signpost pointing toward future exploration. Enceladus becomes another promise, smaller but sharper, because it challenges scale. If a tiny moon can look young, then the outer system may be full of internal heat we have underestimated, waiting behind bland first impressions. Saturn's neighborhood teaches that size alone does not dictate vitality, because architecture can substitute for mass. This is how Voyager changes the audience's map, not by declaring conclusions, but by changing expectations. The outer solar system is not a set of dead satellites around giant planets. It is a network of active worlds shaped by constant exchange. The exchange can be gravitational, chemical, or electromagnetic, and Saturn displays all three in one system. In cosmological terms, Saturn is a reminder that planets do not form alone, and they do not evolve alone. They form with disks, moons, resonances, and long-term interactions that keep systems evolving, even when the initial violence is over. The rings are a visible remnant of disk physics, and the moons are participants in the same continuing story. The choreography is universal, because gravity is universal and disks are common, and that universality is the quiet philosophical payoff. If rings can self-organize here, then structure can self-organize around other stars as well. The question becomes less about whether order can emerge, and more about how many forms that order can take. Voyager's Saturn chapter ends with a deliberate incompleteness that feels almost like a narrative technique. The mission has revealed ring physics and moon complexity, then it leaves the most intriguing surfaces unseen, as if the story is refusing closure. That refusal is productive because it turns the unknown into a defined target rather than a vague mystery. That incompleteness increases the stakes for what comes next, because it reframes the unknown as a pattern. If Saturn is this intricate, then the ice giants ahead may hold surprises that are harder to predict and harder to interpret quickly. The viewer is prepared for ambiguity, because Saturn has shown that clarity often arrives only after new instruments and new encounters. Beyond Saturn, the sunlight weakens quickly, and the solar system thins out in both light and companionship. Voyager leaves the crowded theatre of rings and moons and enters the realm of the lonely ice giants, where distances widen and time stretches. The visuals shift accordingly, less glittering structure nearby, more empty blackness between rare points of light. The signal to Earth will keep fading, and the power budget will keep tightening, turning every observation into a choice. The craft carries Saturn's lessons outward, toward a boundary no camera can photograph, and toward questions that will be answered by instruments alone. Each decision becomes a trade, one more measurement now, or one more year of capability later. The central question remains unchanged, but it now has more weight and more texture. If small moons can be active, then the edge of the sun's domain may also be structured and alive, shaped by forces we have not yet learned to see. Saturn has taught that even thin, delicate systems can carry deep information if we learn how to read their patterns. Voyager moves on, still whispering, leaving behind a ringed world that turned beauty into mechanics. The next encounters will be colder, darker, and even more isolated, and the silence between worlds will become part of the evidence. In that silence, the spacecraft's instruments will keep listening, because in the outer solar system, listening is often the only way to see. Beyond Saturn, the sunlight collapses into a thin, distant glare, and the solar system thins out into long, cold geometry. The familiar brightness that once filled Voyager's cameras is replaced by a hard, slanted illumination, more suggestion than presence. Voyager 1 is already on a fast outbound path after Titan, while Voyager 2 alone carries the grand tour forward into colder arithmetic. The mission's central tension sharpens again as RTG power declines, heaters go dark by design, and margins that once felt generous become ruthless bookkeeping. Every observation now competes with survival, and every watt spent on cameras steals time from the heliosphere story waiting ahead. Even the act of turning the spacecraft becomes a budget line. Torque, propellant, and thermal stability all have a price. In this outer reach, distance is not just a number, it is a filter that erases detail and delays cause and effect. A radio command leaves Earth, crosses the void for hours, and arrives too late for second thoughts. The ice giants were once placeholders on charts, dim disks with few measured facts and even fewer constraints on their interiors. Their remoteness makes them hard to study from Earth, where atmospheric blur and faintness hide subtle structure in cloud bands and rings. Their cold makes them seem simple, as if low temperature must mean low complexity, yet chemistry slows rather than stops. Voyager approaches them as a test of whether the outer solar system is quiet or merely unseen. The central question stays in the background, because these encounters are also rehearsals for reading invisible boundaries. By the time Voyager 2 is committed to Uranus, The mission is already an exercise in long planning and disciplined restraint. Commands are written, checked, simulated, and transmitted across hours of light time, then executed by a machine that cannot be rescued. The Deep Space Network schedules its dishes like a global instrument because every tracking pass is precious and every calibration must be timed. Engineers think in fractions of decibels because the link margin is measured in whispers rather than shouts. Scientists think in fractions of a degree because a pointing error can smear a faint feature into nothing. The spacecraft is small, but the choreography around it is immense, an Earth-sized effort aimed at a moving point. Voyager 2 reaches Uranus in 1986, arriving at a planet that breaks expectations immediately, even before the first close approach. Uranus rotates on its side with an axial tilt near 90 degrees, as if it was knocked over and never stood back up. That geometry turns seasons into extremes, with decades of continuous daylight followed by decades of night across each hemisphere. The sun's weak light still matters, because the tilt changes where it lands and how long it stays on the same latitudes. From a distance, the planet looks like a pale blue-green coin, but its orientation makes it feel like an accident frozen in motion. In the approach images, the disk is calm and softly shaded, and the rings begin to hint at their strange presentation. This sideways spin is not just a visual oddity, it is a dynamical clue written into the planet's angular momentum budget. It implies a violent past, likely a major impact or a sequence of collisions early on, when the solar system was crowded with leftover building blocks. In that era, protoplanets traded momentum like billiard balls, and a single glancing blow could tilt an entire world. A tilted planet keeps the memory of that event in its orientation, long after the debris is gone and the impactor is untraceable. Voyager's flyby turns that orientation into measurable geometry, anchoring models of how planets can be rearranged without being destroyed. The question hangs quietly in the background. How many other worlds seen as calm dots are actually survivors of ancient chaos? Uranus also looks deceptively calm in visible light, with muted cloud contrast and few obvious storms, like a world holding its weather close. The atmosphere is rich in methane, which absorbs red light and leaves the reflected sunlight tinted towards cyan and sea glass green. Thin haze layers soften the planet's features, and the low contrast makes the disk seem almost featureless at first glance. Yet that restraint is itself information, because it implies a different balance of heat, mixing, and photochemistry. That calm forces the instruments to do the heavy lifting, because the physics is not announcing itself in bright patterns. The magnetometer becomes the main narrator, reading the planet's interior through its field. This is where the mission shifts from seeing to inferring again. Uranus's magnetic field is not centered and not aligned with the rotation axis, and the mismatch is too large to dismiss as measurement error. It is tilted by roughly 60 degrees and offset from the planet's center by a large fraction of a radius, pushing the effective dipole away from symmetry. Earth's field is close to a dipole aligned modestly with spin, and Jupiter and Saturn are even more dipole-like in their global structure. Those worlds behave like tidy bar magnets, with poles near the spin axis and a field that weakens smoothly with distance. Uranus refuses that simplicity, and the refusal demands a new explanation. The data reads like a planet with its compass mounted wrong and spinning. A centered dipole suggests a dynamo region organized around the planet's core, where conducting fluid moves in coherent patterns over long times. An offset tilted field suggests a dynamo operating in a shell or in a region that is not symmetric in depth and composition. Voyager's data shows a magnetosphere that lurches and twists as the planet rotates, because the field geometry itself is rotating through space. The result is a magnetic environment that changes rapidly in direction and strength, even at fixed distance from the planet. For a spacecraft trying to interpret plasma boundaries, it is like measuring a shoreline while the tide, the wind, and the map are all shifting. The instruments must separate real structure from motion-induced illusion. That weirdness matters because magnetospheres are boundaries, and boundaries are Voyager's long game. A tilted offset field makes the magnetopores breathe in a complex way under solar wind pressure, expanding and compressing as the upstream flow changes. The spacecraft sees how plasma regions shift, how particle populations change, and how field lines reconnect in bursts that dump energy into auroral zones. It is a smaller version of what the heliosphere will do at a much larger scale, where the solar wind meets the interstellar medium. Uranus becomes a training ground for a future without landmarks. The lesson is that a boundary can be real, measurable, and still constantly moving. To explain Uranus, scientists revisit what an ice giant is made of, because the magnetic field is an interior diagnostic rather than a surface decoration. These planets are not mostly water ice in the everyday sense, and not mostly hydrogen like Jupiter, even though hydrogen still dominates their outer envelopes. They likely contain layered interiors with hydrogen and helium above, then a deep mantle of water, ammonia and methane under high pressure and high temperature. In planetary science, those compounds are called ices, even when they are hot fluids, because they condense as volatiles in the cold outer nebula. Under tens of gigapascals, familiar molecules behave in unfamiliar ways, and phase diagrams become maps of possibility rather than certainty. The words stay simple, but the physics becomes exotic. At those pressures, water-ammonia mixtures can become electrically conductive, especially when ions move freely through dense fluid, rather than being locked into crystals. Conductivity plus convection plus rotation is the recipe for a dynamo, the same basic mechanism that powers Earth's field. If the conductive region is a shell rather than a central core, the resulting field can be multipolar and offset, with higher order components that do not average out. Uranus suggests that the dynamo may be shallow compared to Jupiter's, producing a field that looks lopsided and unstable from afar. The planet's magnetism becomes a clue that the interior is not neatly layered like a textbook diagram. It may be more like a stratified ocean with complicated currents. The same interior picture helps explain the planet's density and its modest heat output, which is a surprise of a different kind. Uranus radiates little extra heat compared to what it receives, unlike Jupiter, Saturn, and later Neptune, and that difference is not subtle. That low internal heat complicates the story, because convection drives dynamos and weather, and convection needs a heat flux to stay vigorous. Scientists consider whether Uranus's interior is stratified, trapping heat and suppressing convection, perhaps through compositional gradients that resist mixing. The planet becomes an argument about how composition can lock energy away, even over billions of years. In a place where sunlight is scarce, internal heat should matter most, yet Uranus seems to keep it hidden. Voyager also surveys Uranus' rings and moons, finding a system that is narrow, dark, and sharply structured, like a set of thin ink lines drawn across space. The rings are not Saturn's bright disk, but they still show confinement and dynamical control, with edges that stay crisp instead of smearing outward. Their darkness suggests particles coated by radiation processing and contamination by carbon-rich material, turning once bright ice into something closer to charcoal. Small moons and resonances shape edges and gaps, repeating the lesson that order is maintained, not inherited. Even here, far from the Sun, the solar system is still actively sculpting itself. The rings look delicate, yet they are governed by relentless orbital math. As the flyby unfolds, the visuals are restrained, but the geometry is dramatic and almost theatrical. Uranus' pole points almost toward the Sun, and the planet's rings present an orientation that feels wrong to the eye, like a familiar object rotated into an unfamiliar frame. The moons pass like small, irregular beads, each with its own history of impacts and resurfacing written in subtle albedo patterns. Voyager's cameras catch faint contrasts, and the team learns to value gradients and limb haze as much as obvious storms. In the background, the magnetometer keeps writing its invisible story, line by line, as if sketching a hidden skeleton. The encounter teaches patience with quiet worlds. The Uranus encounter ends quickly, and the spacecraft's outbound trajectory bends again toward deeper night. The distance to Neptune is vast, and the cruise is long enough for the mission to age in public view, moving from headline spectacle to quiet persistence. Instruments are managed like a dwindling inventory, and the DSN link becomes ever more precious as the signal weakens with the square of distance. The spacecraft keeps whispering, and Earth keeps integrating the signal out of noise, stacking seconds into meaning. Each bit that arrives is a victory over physics, and the victory is never guaranteed. The emptiness between planets becomes part of the story. Between encounters, the spacecraft becomes a lesson in endurance and a study in controlled risk. Thermal conditions drift as heaters are turned off, and components must survive colder regimes than they were designed for on the ground. Lubricants thicken, materials contract, and tiny thermal gradients can matter when power is scarce. software routines become more important, because autonomy is what stands between a minor anomaly and a mission-ending fault. The spacecraft is not just travelling, it is aging, and aging in space is a slow negotiation with entropy. The mission's long arc forces a different kind of attention, less about discovery and bursts, more about continuity. Then, in 1989, Voyager 2 reaches Neptune, and the idea of a quiet outer solar system collapses. Neptune is farther from the Sun than Uranus, yet it looks more active, as if distance has sharpened rather than softened its weather. The planet's atmosphere shows strong contrasts and fast-moving features, with bright clouds that cast subtle shadows on deeper haze. The Great Dark Spot era becomes shorthand for a world with storms that rival the scale of Earth, even if the details shift with time. In the images, Neptune's blue is deeper than Uranus's, a colder, richer tone that makes the white clouds look like brushstrokes. The planet appears alive with motion, despite the dim light. Neptune's winds are the shock, because they are too fast for the available sunlight, and the numbers refuse to be polite. Measured cloud motions imply speeds that can approach or exceed 1,000 miles per hour, racing around the planet in bands and jets. In thin sunlight, solar heating alone cannot drive that much kinetic energy, not without violating the energy budget that governs atmospheric circulation. The atmosphere is spending power from another source, and Voyager forces the accounting to balance. The question becomes unavoidable: what engine is running in the dark? The answer has to be physical, not poetic. Neptune radiates significant internal heat, more than it receives from the Sun, and that excess energy changes everything. That heat can drive convection, which can drive weather, and maintain strong winds by transporting momentum through the atmosphere. Internal heat also helps explain why Neptune looks more dynamic than Uranus, despite being farther away, because it supplies a steady power input independent of sunlight. The comparison becomes a controlled experiment in planetary energy budgets, with two similar worlds producing opposite outcomes. Voyager's brief visit turns them into a paired mystery, linked by class and separated by behaviour. It is one of the mission's most elegant contrasts. The question becomes why two similar-sized ice giants behave so differently when their compositions and masses appear broadly comparable from gravity data. If Uranus traps heat through stratification, Neptune may be better mixed, letting heat escape and power storms that remain visible even in weak sunlight. Composition differences, formation history, and impacts are all candidates, and each implies a different early solar system with different collision rates and migration paths. Voyager does not solve the puzzle, but it defines it with hard measurements and a clear set of constraints. Sometimes the most important result is not an answer, but a boundary on what can be true. Theories must now fit the data, not the other way around. Neptune's magnetic field is also strange, echoing Uranus rather than Jupiter, and the repetition makes the pattern harder to ignore. It is tilted and offset, suggesting a similar dynamo geometry in conductive ice mantles rather than deep metallic hydrogen. Two planets with non-dipolar fields make the class definition sharper, as if the ice giants have their own magnetic dialect. Their magnetospheres are not just scaled-down versions of Jupiter's, but systems with different symmetry and different variability over a rotation. Voyager's instruments register those differences as rotations, abrupt boundary crossings, and particle environments that change quickly. The outer solar system is not a simple gradient of the inner one. That class matters beyond our solar system, because many exoplanets fall into the Neptune-size range, and we often detect them before anything else. Voyager's brief flybys become the foundation for interpreting distant worlds, seen only as transits and spectra, where a planet is a dip in starlight and a hint of chemistry. A non-dipolar field changes how a planet interacts with stellar wind, and how it shields atmospheres from erosion over time. It also changes where auroras might form and how radio emissions might be generated, which matters for remote detection. The ice giants quietly become cosmological data points, linking a local mission to a galactic census. A single flyby becomes a reference for thousands of unseen planets. Neptune's moon Triton becomes the encounter's most unsettling surprise, because its orbit is a confession written in celestial mechanics. Triton orbits in the opposite direction of Neptune's rotation, a retrograde path that is hard to produce in place within a prograde disk. Retrograde motion strongly suggests capture, not co-formation, and capture implies a past that was not gentle. A captured body implies a violent history, where the outer solar system traded objects and energy like a crowded room. Triton is not just a moon, it is a witness. Its very existence argues for a time when orbits were negotiable. Capture is not free because an object must lose energy to become bound, and energy loss requires a mechanism that leaves traces in system architecture. That loss could involve collisions, gas drag in an early disk, or interactions with other moons that were later ejected or destroyed. Whatever the mechanism, it implies Triton arrived from elsewhere, likely from the Kuiper Belt region beyond Neptune, where icy bodies share similar compositions. Voyager's single pass turns Triton into evidence for a larger reservoir of objects beyond Neptune, a population once hypothetical and now increasingly real. The moon's existence makes the outer solar system feel less like a set of neat orbits and more like a history of exchanges. It is a reminder that stability can be the end state, not the beginning. Triton's surface looks young in places, with few craters and varied terrains that change texture over short distances. That youth implies resurfacing, which implies internal heat, because impacts alone cannot erase craters on a global scale without leaving other scars. The surprise is that Triton is small and far from the Sun, yet it is not dead, and its surface is not simply ancient ice. Voyager again finds activity where old models predicted fossilized terrain, and the contradiction is visible in the landscape itself. The images show plains, ridges, and strange patterns that look like frozen flow, as if the surface has been reworked recently. The terrain looks both alien and oddly geological, like a familiar process wearing unfamiliar materials. The most direct evidence is active plumes, geyser-like eruptions rising from the surface, caught in the act by a spacecraft that will never return. The plumes appear to be driven by nitrogen, either sublimating under sunlight or pressurized beneath translucent ice that acts like a lid. Dark material carried by the jets falls back and streaks the surface, making the activity measurable as pattern rather than speculation. Triton becomes a working laboratory for volatile ices, where phase changes can reshape landscapes without molten rock. In the low gravity, the plumes rise high and drift, tracing winds that are otherwise invisible. The scene feels like weather turned sideways into geology. Nitrogen is the key because it is mobile at Triton's temperatures, hovering near a phase boundary where small energy changes matter. Seasonal sunlight can warm dark patches, driving sublimation that builds pressure under a cap, until the surface vents like a release valve. A small amount of energy can move a lot of mass when the volatile is near equilibrium, and that is the plain language lesson. The physics is simple, but the consequences are dramatic because repeated cycles can repaint an entire hemisphere over time. The implications are broad for other icy bodies that store volatiles near the surface. Triton shows that even in deep cold, geology can be active if the chemistry is right. Triton's activity suggests that Kuiper Belt objects may not be inert either, even if they spend most of their time in dim sunlight. If captured bodies can retain volatiles and show seasonal geology, then the outer reservoir is not just debris left over from planet formation. It is a population with climate cycles, surface renewal, and chemical evolution, operating slowly but persistently on timescales we rarely witness. Voyager's glimpse becomes a preview of a region the mission will never visit directly, yet it makes that region feel populated and dynamic. It also raises a quiet question. How many distant objects are changing right now, unseen, while we assume they're frozen in time? The outer darkness may be busy, just at a slower tempo. Neptune's encounter is the last planetary flyby Voyager will ever make, and the ending is both abrupt and inevitable. The grand tour ends not with a planned finale, but with geometry and fuel and time, because celestial mechanics offers opportunities only when planets align. After Neptune, there is no next giant aligned for a close pass, and the spacecraft cannot turn itself into a new mission by force of will. The spacecraft's path becomes a straightening line into the dark, guided by momentum and the sun's gravity rather than ambition. The last close-up world slips behind, and the mission's center of gravity shifts. The story stops being about targets and starts being about a medium. This is where the documentary's emotional and scientific arcs converge, because the story has been building toward a different kind of frontier. The mission has been a sequence of worlds, each one rewriting a rule, from Jupiter's storms to Saturn's rings to the ice giant's strange magnetism. Now the rules are about to change again, because the next target is not a planet with a disk and a limb. The next target is the edge of the sun's influence, a boundary made of pressure, fields, and particles. The solar system, once a set of destinations, becomes a medium to be measured, What does it mean to explore when the object is mostly invisible? Before that pivot becomes official, Voyager 1 performs a final act of looking back, and it is both symbolic and technical. In 1990, far beyond Neptune, it turns its cameras toward the inner solar system, aiming at a region that is now clustered into a small patch of sky. The maneuver is deliberate and costly because it uses time, power, and risk on a gesture, and it also points the camera nearer the sun than engineers prefer. Stray light can wash out detectors, and the optics can scatter sunlight into artifacts that must be understood. It is also a scientific mosaic, a calibration of perspective across multiple frames, with planets placed like markers in a wide-angle map. The spacecraft is not just taking a picture, it is constructing a scale model of distance. The result is the pale blue dot, a tiny point of light that is Earth, and the image is almost aggressively minimal. In the mosaic, Earth is less than a pixel, suspended in a scattered sunbeam created by internal reflections in the camera optics. That sunbeam is not a cosmic spotlight, but an instrument artifact, yet it becomes a visual metaphor that the data cannot avoid. The image is not a portrait of continents, it is a measurement of scale, and scale is a scientific quantity. It shows how small a habitable world appears from the frontier, and it shows how easily that world could be missed. The photograph makes a familiar place look like data. The emotional weight is unavoidable, but the science is not optional, and the two are not enemies. The dot is a reminder that all planetary data came from one location, one atmosphere, one biosphere, and one fragile platform for curiosity. It is also a reminder that the spacecraft's instruments are finite, and that the next decades will require different priorities and different kinds of patience. In practical terms, the mosaic also closes a chapter of optical exploration, because cameras demand power, data rate, and stable thermal conditions. The image becomes a hinge between planetary science and heliophysics, between landscapes and plasma. It asks a question without words. What does it mean to map the universe when your home is smaller than a pixel? After the pale blue dot, the cameras are turned off, not because curiosity ends, but because resources do, and the decision is both practical and irreversible. The decision preserves power and reduces risk to systems needed for the interstellar objective, because cameras are hungry for energy and thermal stability. It marks the end of the planetary era for Voyager, closing a chapter of colour and texture that defined a generation's imagination. It also marks a commitment to the central question that has been waiting behind every encounter, quietly gaining weight with every mile. The mission chooses invisibility as its next subject. The silence of the cameras is not an ending, but a reallocation of attention. The mission becomes about fields and particles, not pictures, and the change is more profound than it sounds. Magnetometers, plasma wave instruments, and charge particle detectors become the eyes, translating invisible phenomena into voltages, spectra, and counting rates. Voyager becomes a drifting test particle in the sun's outflow, measuring gradients rather than landmarks, and that is a different kind of exploration. The spacecraft's path is now a transect through an invisible structure, where meaning comes from correlations between instruments rather than from a single frame. The reward is not an image, but a boundary crossing confirmed by multiple signatures. In this phase, discovery sounds like a change in tone and a shift in statistics. That structure is the heliosphere, the solar wind bubble inflated into interstellar space, and it is shaped by motion and pressure rather than gravity alone. It is not a perfect sphere because the interstellar medium pushes back, and the sun's magnetic field twists into a Parker spiral carried outward by the flow. The boundary is layered, with shocks, turbulent regions, and changing particle populations that mark transitions in plasma regimes. The termination shock slows the solar wind. The heliosheath becomes a region of compressed turbulence, and beyond lies the heliopause where pressures balance. Voyager's job is to measure where the sun's rule stops dominating, and where the galaxy's background becomes the local weather. The frontier is not a line on a map, it is a region with thickness and structure. The ice giant encounters matter here because they taught Voyager how to read invisible borders, and they forced the team to trust in direct evidence. Uranus and Neptune showed that magnetic geometry can be strange, and that plasma boundaries can be dynamic, moving even when the planet itself is steady. They trained the mission teams to trust field rotations, particle dropouts, and wave signatures, because those are the fingerprints of crossings. Those are the same kinds of clues that will define the heliopause, where the solar wind yields to interstellar plasma. The planets were lessons, and the heliosphere is the exam. The skill is the same, only the scale changes. The countdown in watts becomes the story's constant metronome again, and it is as relentless as orbital mechanics. As RTG output falls, heaters are shut down and instruments are triaged permanently, with choices that cannot be undone once systems cool and materials contract. The spacecraft must keep pointing its high-gain antenna at Earth, spending hydrazine and managing thruster wear with careful pulses that avoid introducing unwanted spin. Safe mode remains a lurking threat, because a fault could break the link for hours, then days, and recovery is never guaranteed at these distances. In deep space, silence is not peaceful, it is alarming. The mission learns to fear missing data more than bad news. The Deep Space Network becomes part of the narrative again, because the signal is now unimaginably faint, a whisper stretched across billions of kilometers. Earth's antennas integrate longer, receivers improve, and schedules tighten, because the spacecraft competes with other missions for tracking time. The spacecraft's carrier tone becomes a lifeline and a scientific tool, because Doppler shifts and phase stability carry information about motion and link health. The whisper is still coherent, and coherence is what makes measurement possible when the noise is higher than the message. In a sense, the DSN becomes an extension of Voyager's instruments, completing the circuit across space. The exploration is shared between a machine in darkness and a planet listening carefully. With the planets behind, Voyager's meaning shifts from exploration to cartography of a boundary, and the boundary is protective in a way we rarely notice. It is mapping the Sun's domain in situ, one data point at a time, building a profile of plasma density, magnetic orientation, and energetic particle behavior. It is also mapping our place, because the heliosphere is a kind of temporary shelter, deflecting some fraction of galactic cosmic rays. Its size and porosity shape how cosmic rays reach Earth, influencing radiation environments over long timescales and possibly interacting with climate proxies. The mission's late phase is quiet, but it is not small. It is the slow measurement of a cocoon. The chapter ends on a turning point that feels like a farewell and a beginning, because the last photograph is both an ending and a reference frame. The last photograph is a reminder of what is being left behind, and of how quickly familiar worlds shrink into abstraction. The next phase is a confrontation with a frontier that cannot be photographed, only inferred through patterns in fields and particles. With the planets gone, the real this begins, and it begins at the edge of everything the Sun can hold. The story becomes less about destinations and more about thresholds, where the universe changes character without changing scenery. Voyager travels on into a region where the Sun's wind slows, heats, and becomes turbulent, and those changes are signatures of approaching the boundary. The spacecraft is now committed to the long, quiet work of boundary finding, where progress is measured in gradients rather than miles, and where patience is a scientific method. The central question is no longer philosophical, because it is about to become measurable in instrument readouts and sudden transitions that cannot be mistaken. The next chapter will follow the instruments into the heliosphere's final gradients, where outside is defined by physics, not by distance. In that darkness, Voyager will keep listening for the moment the Sun's influence finally thins into the galaxy. The planets are gone, and Voyager's subject becomes the space between worlds, where emptiness turns out to have texture. The central question tightens into a measurement problem, because distance alone is not a border. Where does the Sun's domain end, and what does outside feel like when you can only sense it indirectly? The Sun fills space with a continuous outflow called the solar wind, streaming from the hot corona at hundreds of kilometers per second. It is a thin plasma of protons and electrons, threaded with an embedded magnetic field that rides outward with the flow. Because the Sun rotates, those field lines are wound into the Parker spiral, an invisible pinwheel that stretches across the solar system. That outflow inflates a cavity in the surrounding galaxy, pushing back the local interstellar gas and dust like breath against fog. We call it the heliosphere, and it is our local space climate, complete with storms, seasons, and long-term trends. It matters because it deflects and slows some incoming galactic cosmic rays, which are high-energy particles accelerated by supernova shocks and other violent events. It also sets the radiation and plasma environment that every planet lives inside, shaping auroras, atmospheric loss, and the hazards faced by spacecraft. For decades, the heliosphere was drawn like a simple bubble, almost like a glass sphere around the Sun. Early models assumed a clean boundary where solar influence stops and interstellar space begins, because that was the simplest way to think. Voyager was built to test that picture with instruments, not metaphors, and to turn a cartoon edge into a physical profile. The first boundary is the termination shock, and it is less like a wall than a sudden change in the wind itself. Far from the Sun, the solar wind can no longer outrun the pressure pushing back from the interstellar medium. The flow slows abruptly from supersonic to subsonic, and its energy shifts into heat, turbulence, and particle acceleration. Beyond that shock lies the heliosheath, a thick, compressed transition region where the slowed wind piles up and circulates. Here the plasma is stirred and mixed, and the magnetic field can fold back on itself in tangled arcs. Particles are accelerated into energetic populations, and conditions change with solar activity that began years earlier near the Sun. The outer boundary is the heliopause, which sounds like an edge but behaves more like a negotiated truce. It is not a hard shell, but a pressure-balanced surface where outward solar wind pressure meets inward interstellar pressure. On one side, the solar wind dominates, and on the other side, the local interstellar medium dominates, yet the interface can still be structured. Voyager approaches these layers like a drifting test particle, small enough to be carried by the environment it measures. It cannot see the boundary, so it reads it in gradients, slow trends interrupted by sharp steps. Charged particle counts, magnetic field strength, and plasma waves become the map, and each instrument is a different sense. Voyager 1 reaches the termination shock first in 2004, and the crossing arrives as a change in the wind's character. The data shows the solar wind slowing and heating, and energetic particles increasing as if a reservoir has been opened. The crossing is not a single moment because shocks ripple, reform, and shift with upstream conditions. Voyager 2 crosses the termination shock in 2007 on a different path, and the later time is a clue. The timing difference reveals asymmetry, not error, because the heliosphere is not a perfect sphere. The Sun's bubble is squashed and tilted by the interstellar flow and magnetic pressure, like a sail pressed by a steady breeze. This is the first major surprise that resolves earlier hints from remote measurements and theory. The Sun's bubble is not centered and not steady, and it cannot be described by a single radius. It is shaped by the Sun's 11-year cycle, and by the galaxy's changing upstream conditions as the solar system moves. As the probes push outward, the instruments show a heliosheath that refuses to behave like a quiet buffer. Particle populations vary in bursts, suggesting turbulence and transient structures moving past the spacecraft. Magnetic fields strengthen and fluctuate, and the boundary seems to breathe, expanding and contracting as solar pressure rises and falls. The deep space network keeps the whisper alive through long integrations, careful Doppler tracking, and antennas that must aim with exquisite precision. Every bit arrives late, faint and precious, carried by a signal that has spread thin across billions of kilometers. The countdown in watts turns each year into a trade between measurement and survival, and engineers must choose what to keep warm. In 2012, Voyager 1 reaches the heliopause region, where the data begins to look unfamiliar. The key signature is a sharp drop in heliospheric particles, the ones born in the solar wind and shaped by the heliosheath. At the same time, galactic cosmic rays rise and stay high, as if a door has opened and stayed open. The team expects another clear sign because textbooks suggest an obvious magnetic handoff. They expect the magnetic field direction to rotate dramatically, because interstellar field lines should differ from the Sun's spiral. Instead, the direction changes little at first, an anticlimax that triggers debate and forces a careful recheck of assumptions. If the field does not turn, are we really outside, or are we still inside a solar structure that only looks like the edge? Or is the boundary more complex than the diagrams, layered in ways a simple sketch cannot show? The answer arrives by combining imperfect instruments into a coherent crossing story, where each data set supports the others. Voyager 1's plasma instrument failed long before, so density must be inferred indirectly, like listening for wind through a closed door. Plasma wave measurements detect oscillations driven by shock events that propagate outward from solar eruptions. The frequency reveals electron density, and the density matches interstellar values rather than the thinner heliosheath. That density jump becomes the ground truth, because density is a defining property of the medium itself. Voyager 1 is in interstellar plasma, even if the magnetic geometry looks familiar at first glance. The heliopause is not a clean cut between two unrelated fields, and the transition can preserve alignment over local scales. The best explanation is magnetic draping and coupling, a process that is intuitive once you picture the flow. Interstellar field lines can wrap around the heliosphere, aligning locally with the heliospheric field as they are diverted. The interface can be layered, porous, and threaded by reconnection, events where field lines break and rejoin, allowing energy and particles to cross. Porous does not mean open like a hole in a wall, where everything simply spills through. It means transport can occur along complex pathways, depending on turbulence, field topology, and the gyrating motion of charged particles. Some particles leak across, and some are trapped, and the balance shifts with time as conditions evolve. This is what Voyager found at the edge, and it changes how the heliosphere should be imagined. The boundary is dynamic and structured, not a static shell drawn with a single stroke. It responds to solar eruptions that propagate outward for years, and it also responds to interstellar pressure that is always present and never negotiable. In 2018, Voyager 2 reaches its own heliopause crossing, providing a second line through the same frontier. This time, the plasma instrument still works, and it measures the solar wind directly as it fades. The data shows the same pattern of particle drop and cosmic ray rise, and it confirms a density increase consistent with interstellar space. The two crossings do not match in distance or detail, and that mismatch is the point, not a problem. Voyager 1 and Voyager 2 approached from different latitudes and longitudes, sampling different parts of a distorted boundary. The heliopause moves, and it is warped, and it is different in different directions at the same time. Solar cycles help explain the timing, because the solar wind's pressure is not constant across decades. When solar wind pressure is higher, the heliosphere expands outward, and the termination shock can shift. When it weakens, the boundary contracts, and the heliosheath changes thickness and turbulence, like surf responding to a changing tide. Interstellar conditions also matter, and Voyager finally gives them a local address instead of a theoretical label. The Sun is moving through a patch of the local interstellar medium, a partially ionized mix of gas, dust, and magnetic field. That medium has its own density, temperature, and field orientation, and it presses on the heliosphere like a steady wind. This places the story inside the galaxy, not outside it, because interstellar space is an environment with structure. The heliosphere is one astrosphere among many, shaped by the same physics that surrounds other stars. Every star with a wind inflates a cavity, and those cavities can collide, distort, and overlap in complex ways as stars drift. Voyager turns that idea into calibration, which is rare in astronomy and therefore valuable. Models of astrospheres around other stars rely on remote inference, absorption lines, and simulation, because we cannot visit them. Voyager provides in situ measurements of shocks, turbulence, and magnetic draping that those models must reproduce, or else be revised. The cosmology context is quiet but consequential, because cosmic rays are not just background noise in a detector. They are a galactic weather system, influenced by magnetic fields and accelerated and energetic astrophysical sites. The heliosphere modulates that weather, and its changing shape changes the shielding we experience over long times, with implications for atmospheres and biology. The documentary's earlier boundary lessons now pay off, because the solar system has been teaching this language all along. Jupiter's magnetopause taught that invisible borders announce themselves through particles and fields, not through visible lines. Saturn's rings taught that sharp edges can be maintained by ongoing dynamics, and the heliopause combines both lessons at the largest scale we can physically sample. Now the mission enters its long fade, and the visuals shift from dramatic crossings to patient endurance. RTG power continues to decline as plutonium decays, and heaters and instruments are shut down one by one. Each shutdown is irreversible, because cold and power loss can make restarts impossible, and because the margin is measured in single watts. The spacecraft still must point its high-gain antenna at Earth, holding a narrow beam across a widening gulf. That requires hydrazine and careful attitude control, with tiny thruster pulses that must be rationed. Safe mode remains a threat because a fault could break the link, and the light time makes recovery slow and uncertain. In the 2020s and beyond, the remaining instruments become a minimal listening post, taking the pulse of particles and fields in the dark. Eventually the power will drop below what the transmitter and core systems need, and the signal will thin. The carrier will vanish into noise, and Earth will hear nothing back, even though the spacecraft still exists. Silence will not mean the mission stopped, because motion does not require communication. Voyager will keep moving on its outbound trajectory for tens of thousands of years, coasting through the local interstellar medium. It will drift through new regions the Sun has not yet reached, and through conditions that may differ subtly in density and field strength. Cosmic timescales enter gently, then land with weight, because the numbers stop fitting human intuition. Human history is shorter than the travel time to the next star, even at Voyager's enormous speed by everyday standards. Voyager's journey continues anyway, because momentum does not require purpose, and the galaxy does not pause for witnesses. So what did Voyager find after nearly 50 years into space and beyond the last planet's light? It found that the edge is not a wall and outside is not empty, even when it looks black. The Sun's last breath meets the galaxy in a shifting frontier that can be measured, and that frontier has structure worth naming. The final synthesis is both scientific and existential, because the same data can carry two kinds of meaning. Physics leaves readable signatures even in darkness if you carry the right instruments and wait long enough for the gradients to appear. Two machines built for a few short years became our first physical connection between a planetary civilization and the Milky Way. The whisper fades, but the trajectory remains, and the camera can linger on a receding point of light. Voyager travels on as a message in motion, not just a record on copper, and not just a triumph of engineering. It proves that our solar system is a temporary breathing island inside a vast galactic ocean, and that even the ocean's shoreline can be surveyed. For nearly 50 years, Voyager has been two things at once: a planetary explorer and a faint, disciplined whisper in the deep space network. It showed us violent, living worlds, Io's fire feeding Jupiter's plasma engine, Europa's fractured ice hinting at hidden oceans, Saturn's rings behaving like a restless disk, and ice giants with magnetic fields that refused to sit neatly at their centers. And when the cameras went dark and the watts began to vanish, the mission's real map emerged, drawn in charged particles, magnetic fields, and plasma waves, an atlas of an invisible moving solar frontier. The grand tour only happened because gravity and timing briefly cooperated, and the spacecraft only survived because engineers treated time itself as an enemy to manage, one heater and one bit flip at a time. Each flyby became rehearsal for a larger lesson, that boundaries in space are rarely lines you can photograph, and almost always regions you must infer. Jupiter's magnetopause trained us to read the unseen. Saturn's elegance hid dynamic physics. Uranus and Neptune taught us that even quiet worlds can be strange and energetic, and the pale blue dot reminded us that the most important perspective shift is often the smallest image. In the end, Voyager became what it was never advertised as, a pair of test particles drifting outward, measuring the Sun's influence by how it yields. What it found at the edge was not a wall, but a layered negotiation between pressures, fields, and flows. The termination shock was not the clean breaking point we imagined, and the heliosheath was not a uniform moat, but a turbulent, time-lagged region that remembers old solar storms. Then came the heliopause, a boundary that should have announced itself with a tidy magnetic turn, yet instead arrived as a paradox. Heliospheric particles collapsing, cosmic rays flooding in, and magnetic fields that seemed to drape rather than snap. Voyager. One forced scientists to argue from missing plasma data, using particle dropouts, cosmic ray rises, and plasma wave, inferred densities as a fingerprint, while Voyager 2, with its working plasma instrument, confirmed the crossing in a different place, at a different time, on a different cut through the same breathing structure. Those mismatched crossings were not a failure of prediction, they were the discovery. The heliosphere is squashed and asymmetric, sculpted by the local interstellar flow and magnetic pressure, and it expands and contracts with the Sun's 11-year cycle like a lung. Its edge is porous enough for reconnection and mixing, yet firm enough to mark a real change in density and radiation environment, and that combination, measurable yet not fully knowable, is the signature of a true frontier. Beyond it, the local interstellar medium is not empty, but thinly populated, magnetized and variable, a sea with currents we have only tasted in the first few samples. All the while, the story has been a countdown, not to an explosion, but to silence. Every year the RTGs cool, the electrical budget shrinks, heaters are sacrificed, instruments are powered down forever, and the spacecraft's ability to keep its antenna locked on Earth becomes more precious than any single measurement. Safe modes and recoveries have been quiet cliffhangers, a subtle change in a carrier tone followed by hours of light time and days of careful diagnosis, reminding us that the link itself is part of the experiment. And still, across billions of kilometers, the DSN integrates and subtracts and predicts, turning noise into meaning, keeping two aging machines just barely within reach long enough to finish the most distant field study in human history. The unresolved threads remain, and they are not loose ends so much as open doors. Saturn's rings still challenge our sense of age and maintenance. Titan's hidden surface still invites new eyes. And Enceladus's brightness was a hint that later missions would confirm with geysers and an ocean. Even Voyager's Interstellar chapter has only begun, because the local interstellar medium is structured, and the spacecraft will drift into new regions over tens of thousands of years, long after their transmitters go quiet. What we call outside will keep changing, not because reality shifts, but because our measurements will. In that way, Voyager's greatest revelation is not a moon, a storm, or a photograph, but a redefinition of home. The solar system is not a static kingdom with a fixed border. It is a temporary breathing island, carved by a star's wind and pressed upon by a galaxy's weather. The edge of the sun's domain is real enough to cross, but alive enough to move, and that is why two spacecraft could leave on the same mission and still meet the frontier on different terms. Call back to the opening hook. What did Voyager actually cross out there? And what else have we been wrong about? It crossed a boundary that behaves less like a fence and more like a shoreline, where the sun's influence fades through layers, leaks, and magnetic negotiations rather than ending in a single stroke. And if we were wrong to draw the solar system as a neat bubble, we should be cautious about every clean diagram we inherit, because nature prefers gradients, not absolutes. Final thought. Voyager did not find the end of our world. It found the fact that our world has an edge that can be measured, argued over, and still remain mysterious. When the last watt is spent and the last carrier dissolves into noise, the spacecraft will keep flying, silent messages in a larger ocean, reminding us that exploration is how a small planet learns the shape of its own belonging. Call to action. Keep listening, keep building, and keep asking better questions, because the next boundary will not announce itself until we dare to measure it. It crossed a heliopause that behaves like a shoreline, not a wall, and its shifting asymmetric crossings reveal how provisional our neat borders really are. If the sun's frontier was never where we drew it, then every edge we claim to understand deserves another measurement and another doubt. Voyager's greatest discovery is that our solar system is a breathing island, its border measurable in data yet profound in mystery. Long after the signal fades, its trajectory will still say the same thing. Home is not a place we finish defining. Stay curious, support the listening networks and the next interstellar probes, and treat every clean cosmic map as an invitation to test it.